2 minutes we started. I think the microphone is green. I think estamos mejor abajo porque si no lo vemos. If she need to water, but no, there is not place to.
There's no place. No, I don't know.
No, the table is not buena esa mesita.
Yeah.
Good morning, everybody. We're going to start with the plenary session of Professor Biao Jung. He will share with us his research activity respecting the advancing causal analysis for fault detection and root cause analysis in process system engineering. And let me introduce him saying a little bit about his CV. Professor Wang obtained his PhD in control process from the University of Alberta in Canada in 1997, and had the master degree and the bachelor degree in automatic control for the Beijing University in aeronautic and astronautic. And he joined the University of Alberta in 1997 and as assistant professor in the Department of Chemical and Material Engineering, which he's continued working there. And he's now currently a full professor and senior University of Alberta Engineer Research Chair in Smart Automation. He held the position of Senior of Industrial Research Chair, and he's a EEE Fellow for the Canadian Academy of Engineering, Fellow of the Chemical Institute of Canada, a recipient of Germany Alexander von Humboldt Research Fellowship. His research interests include process data analysis, as we can see here, machine learning, system identification, imaging processing, fault detection and isolation, and soft sensor. Currently, Professor Wang serves severe editor responsibility as a co-editor, and he was for the Journal of Franklin Institute, Associate Editor of the EEE CAA, and Associate Editor of the Journal of Process Control. And he served as the editor-in-chief of the IFAC Journal of Control Engineering Practice, and he's presently as its honorary editor. Please, Professor Wang, you have the word, please.
Thank you. Okay, that's good. So thank you for the kind introduction. And today I'm going to talk about the causal analysis for fault detection and root cause analysis, specifically for process system engineering. So I'm talking about advanced technique from evolution from basic one to the advanced one. So my talk is outlined as follows. I'm going to start with recap of what is causal analysis. Of course, it's very obvious. And then I talk about the fundamental, which is the granular causality causal analysis. And then followed by the sparse granular causality analysis. Then I introduce this advanced technique called physics-informed sparse causality analysis. And then I'm going to give two examples, which are real applications or industrial applications, to end up my presentation. So I'll talk about causal analysis. And of course, the most famous one starting from the chicken and the egg and which one come first. And I've been debated for a long time, but it doesn't really matter. It's really one of the cause others, or they just correlation. So look at what is correlation. So very often people get confused between the causation and the correlation. So here's the small cartoon demonstrating that the correlation doesn't really imply the causation. So they're not the same thing, which often confuse us. Now, so what is the correlation? So what difference between correlation and the causation? So first of all, I know we see that causation is any cause that produces an effect. And the correlation really measures the relationship between two different things. Now I give example to demonstrate the difference. So at some time point, I think it's in UK somehow, they say in certain time period, the production of refrigerators increased, but in the same time, the crime rate increased. So question is that does this production of refrigerator cause more crime rate? This is not really the causation, but they are correlation, meaning that they depend on some other factor which generate the increase in the two different variables. So it's correlation, not the causation. Anyway, so in this causal analysis, and often people focus on so-called deterministic causality. For example, like a light switch turned on, and you see the light bulb on. So this is almost like deterministic. We're going to want it to happen. So this most case we study this deterministic causal analysis. But there's another type of causal analysis or causation, which we call probabilistic causality. So for example, and this kind of causal relation, they have some uncertainty. So typical example is smoking was lung cancer. So we know in the statistically, smoking will create lung cancer in the long term. However, some people smoke whole life, they still live for a long, long time. So it's not always true, but in most cases they're true. So there's uncertainty with this causal relationship. Now this cartoon says that, so that this basically patient look for the diagnosis by himself, looking at Google search, and with a lot of uncertainty. The doctor believes that because he learned, he got a medical degree, and he knows better about this diagnosis. But is that true? We all know that they're not necessarily true. Meaning one of diagnosis may be better than other one, but not necessarily always deterministic. So it's always stochastic or with uncertainty. Now the further complexity comes from the causal relationship. Okay? Not necessarily to be direct. So for example, A cause B is direct, so meaning that it's obvious, so it's clear. So A is the cause of B, and so that is easy one to, the most of study focus on this direct causal relation. However, there's another type of causal relation called indirect. So in an important case that you have A does cause B, but it doesn't directly cause B. It goes through another factor called C, then cause B. It looks like a simple from this simple relationship. However, in reality, this can create a lot of challenging or uncertainty in causal relationship. So I give an example of this cartoon. So it says that it's cold. Okay, so getting cold, we know, and over a year, and with some locations in Europe and in North America and so on, getting really cold. So does that mean the global warming doesn't exist? Okay, so basically, this is the typical example of the indirect causal relation. In other words, global warming not necessarily directly cause the cold or specific location. It may introduce the change weather pattern, El Nino, and so on, and they create this cold pattern weather. So that's intermediate, the indirect result. Global warming causes something else, and something else causes this cold weather in some particular location. Okay? So that complex make a causal analysis more complex, sometimes maybe contradictory to each other. So again, so the challenge in this causal analysis, as we said, one's complexity and also data limitations. And often these causal analysis are based on data driven. So based on data we have, and we do modeling and find a causal relation. So many data driven. So the data requirement certainly is important, but we have limited data in terms of valid or less noisy data, which we don't have many for particular processes or systems. So there are some confounding factors which can create some apparent causal relation, which makes things complicated. And also computation resources. Now people are starting using this machine learning to do a causal analysis, which of course needed a lot of computation resource. And interpretation challenging, which very often, and how to interpret the result we obtained from this database causal analysis. So here's the example of the complexity in causal analysis, a cartoon, and it says it's dark. So let's say the sun doesn't exist. Okay, so this is actually not true, and we know it. So sun does cause this light in the daytime, but evening you can not see relationship between sun and the light. So it really says causal relation can change over time. So it's, again, make things more complicated in determining the causal relationship. Now, I gave the introduction about the motivation to the causal analysis. Now, the most fundamental causal analysis or study starting from the granular causality, which is very famous theorem about causal relationship. So granular causal relation defined in the following way. So it says that the cause happens prior to the effect. So in a time sequence, cause come earlier and the effect come later, which of course makes sense. And the cause has unique information about the future of its effect, meaning that if this variable is a cause, it must be unique. There's no second variable which have similar or same effect. So based on this assumption, so actually this is the name after Nobel laureate Cliff Granger, after his name. So based on this, and we have this, so again, the assumption, because at that time, last century or 2 centuries ago, and the computation resource is limited. So there are some assumptions about how to use the granular causality to do the calculation. So there's some assumptions. So first of all, the data must be stable or stationary data. And no omitted variable. All variables which are interest must be included in the causal analysis. And also, because the limitation, the time for the modeling, so assume the causal relation is linear dependence. And with lack of there must be no external shocks. Okay, so these 4 assumptions made for this granular causal analysis. So the idea is simple. So basically, as a definition of causal analysis. So first of all, we build the first model, okay, model 1. So in model 1, we want to know what is the cause of YT. So YT assumes effect. We want to find its cause. Okay. So, and of course, when we build a model, we know YT also dependent on itself because autocorrelation. So meaning YT depend on YT minus 1, YT minus 2, and so on. So we build a model, okay, based on itself and this first model. Now we suspect this X is the cause of Y. So include X in the second model. So your X really can explain this Y as cause. Then this model, by including this X, we expect model 2 will be better than model 1. So in the sense of the modeling error with residual, so residual E2 should be smaller than E1 if X does cause Y. Okay? So you can see a comparison of variance of residual, we can determine if X granular cause Y. Okay? So that's a very simple idea to do this. Of course, we can do a rigorous derivation about some test. So the test with H0 will be lagged value of X do not cause Y, so H0. H1 means lagged value of X granular cause Y. But because in this case, everything is linear, okay, which is a good assumption, so we're able to derive some nice expression to determine which model is better. Okay. So basically, you can derive the test rigorously as this F distribution. Okay. So F distribution says in the numerator, this RS1 is the model 1 error, RS2 is model 2 error, a denominator more or less a normalization anyway. So this F distribution, so we can see if the 2 models are similar to each other, this F value will be closer to 0. Okay? If model 1 has much larger error than model 2, or model 2 has much smaller error than model 1, so X does cause Y. So you can see the difference will be larger and F will be larger. So you can see, by compare the value of F to be larger or smaller, we can determine if there's causal relation between X and Y. Okay? Now, of course, this threshold value, how small is small, how large is large, because we have this nice expression, and you can find from the F table of the statistics table, you can find the threshold value to determine if there's causal relation or not. Okay. Now, when we look at more than two variables, so we have multiple variables, we have P different variables, we want to find a causal relation. It's a bit more complicated, but not bad. So what we do is that we're going to build a model. In the left-hand side is P variables. Right-hand side, you have XTD. Again, P variables with lag, all past value with lag. So X1 with lag from 1 to D, and so on. Okay? And this M represent the relationship or coefficient. So basically, by looking at this M value, we're able to know if there's causal relation. For example, if M1P equal to 0, then there's no causal relation from X1 to XP. So now problem come out, simply look at the coefficient of this M matrix and to see if there's any causal relation or not. Okay? Now, to solve problem, it's actually a simple solution. It's just really least squares. So least square solution, we minimize the error, sum square error of two norm. We're able to estimate M based on data we have. So, and then check M to see which part of M equal to 0, then find the so-called non-causal relation. Non-zero means like causal relation. So it's simple, conceptually very simple. But there are limitations in this type of analysis. For example, more variables, meaning that when we look at this least square solution, this M, all of them are non-zero, meaning that once you solve it, believe me, and M, all elements are non-zero. So really say you don't have any variable has no causal relation. So that is problem, many variables. And also, you have spurious causal relation because none of them is 0. And difficult to interpret, you got all causal related, and you cannot interpret at all. Now, for that reason, and the theory evolved into so sparse granular causality, causal analysis, and the sparse one. Okay. Now, for sparse causal analysis, and of course, by definition, by intuition, sparse will provide better solution because with sparse, you get a variable reduction, okay? And you have better interpretability and improved generalization, reduced complexity because sparse means that the model quality will be higher. So how to introduce sparsity? So I did again simple, and you really, the first term is still same as before the least squares. And the second term is regularization term, which regularize this magnitude M. And use one norm, you get a sparse solution. And why one norm gets sparse solution, we can talk later. But anyway, so this L1 regularized regression, also called Lasso, which is also very famous regression. And this parameter lambda can be tuned. You want more sparse, you can increase lambda value, but this becomes subjective. So we'll talk later on how to solve the problem. And this sparse regression will encourage small coefficient of M to be 0, to be clear. So because if that's small, it's forced to be 0. Okay. Now, why this L1 norm can improve sparsity or introduce sparsity? So here's the demonstration, simple demonstration. So think about L1 regularization can be expressed by suppose two parameters, beta 1, beta 2 equal to R. So this green colored one. Okay, has this shape. And this part, the contour like a least squares, okay, minimize the error. So you can think this solution, minimization solution is when you expand this contour, the first time these two shapes get in touch, okay, then that's the solution. So you can see when it expanded and get in touch, which really at the corner, okay. At the corner location, you can see beta 2 is non-zero, beta 1 is 0. So meaning that two parameters, one of them becomes 0. But if you look at two norm, okay, the square, if regularization two norm is like ellipse or the circle, then when they get in touch, it's unlikely they got to encounter somewhere. So they have beta 1, beta 2, both are non-zero. So that indicate why L1 norm will provide sparse solution. Now, sparse solution or granular solution still have limitation. So for example, because it's subjective and it has a chance to remove all the causal, real true causal relation can be removed, it still requires a large amount of data to do it. Okay. So that reason I now introduce this currently become very popular way to the machine learning community, which include the physics-informed causal inferencing or causal relationship. So in this case, I know we have basically, for all this database analysis, our question is that the result is reliable or not reliable. How do we know? And the causal relation, and typically we do have a lot of physical information, meaning that we have some prior knowledge about the causal relationship. Okay. So can we really include what do we know about the system process in the causal analysis? So that is physically informed approach. So how to include this prior knowledge? Again, so collaboration between machine and a human being, and through this causal analysis to produce more reliable causal map. And of course, this will be more accurate and more reliable and easy to interpret because include physical information. And of course, more robust to limit the data because we have fewer parameters to estimate. And because include physical information, so have collaboration between different discipline field, different expertise can all come together and to come out to the final causal relation. Now the solution actually not too complicated, actually simple, pretty intuitive. As we mentioned that we already have this called the sparse causal analysis objective function, L1 norm. Okay? Now by including the constraint, okay, such as equality constraint or inequality constraint, we're able to get the physics information to be included when we do the modeling process. Okay? So for example, suppose we have two variables, x1, x2, this side a lagged variable, here's coefficient. Now, if we know that this coefficient to be 0, meaning that the relation between x1 and x2, if we know there's no causal relation between first variable to the second variable, then can enforce the constraint on this coefficient M1, M2, M22, that corresponding to lagged x1 variable. Okay? So like you can enforce it or just let it set it to 0. Okay? Similarly, if you know there's causal relation between x1, x2, meaning that we know x1 does cause x2, then we can force these two parameters to be non-zero to set a small value sigma and make it inequality. So by doing that, we're able to include both equality and inequality into the constraint to optimize the solution. So now, the new question, new problem introduced because doing this. As we mentioned earlier, if we have linear relationship, okay, we have nice data, stationary data, we can nicely derive some analytical expressions such as F-test. Okay? So we can easily find the F table and to determine the threshold value and then determine the causal relation. But now the things become much more complicated. We have introduced this sparse causal relation. We also include this physics information constraint. The original nice derivation of this threshold value no longer exists. Okay? You cannot find nicely from any table. So the way to do it is through the so-called surrogate data analysis, okay, to determine the threshold. And how we do it? So basically, we generate the surrogate data set. Okay? This data set will preserve certain statistical property of original data. But meanwhile, it destroys the relationship. Okay? So let me demonstrate how do we do this. Suppose we have two variables, A and B. We want to find a causal relation, A to B or B to A. Okay, but we don't know yet. Okay. Now, how we do it? So basically, we can start doing so-called surrogate transfer. So basically, we transfer map A to A tilde, B to B tilde. So by this transformation, we ensure that there's no correlation between A tilde and B tilde. No correlation. We don't care about causal or non-causal. No correlation. No correlation means no causal relation. So we really destroy this correlation between A and B through A tilde and B tilde. By doing that, so we know there's no correlation in this A tilde, B tilde, and there's no causal relation. between A and B, A tilde and B tilde. Then we build a model, same model as we did earlier, build a causal model. But the model between A tilde and B tilde, the corresponding M will indicate that no causal relation. So let M must be small value. That M value can be used as threshold value to do the threshold to determine if there is a causal relation between A and B. Basically, use this information to determine the threshold value, then back to original data, A and B, determine whether or not the M value between A and B is 0 or not by comparing with this threshold. So that approach, so-called surrogate data analysis approach. Now, how to destroy the relationship between A and B? There are many different ways. For example, such as pose, phase randomization, amplitude adjustment, and so on and so forth. You can really destroy the relation between two variables. Okay. Now, the problem we often face in the process, in the systems, is the oscillation. So that's oscillatory behavior of the system. And oscillation typically caused by some problem in the instrumentation or the process. Okay. So we want to know any causal relation with some oscillation. Of course, here I idealize by pure sinusoidal wave, but in reality, there's noisy sinusoidal wave. We want to find a causal relation. Okay. Now, how to do this? Now, for this sinusoidal wave, how we perform the surrogate transformation to destroy the relation between two signals. It's difficult for sinusoidal wave. No matter how you do, they are always correlated. So the way you do it, and the thing about these two signals, okay, sinusoidal wave, okay, idealized pure sine wave. So you do the correlation between two signals. The correlation also sinusoidal wave, okay, also wave. At some point, you can see the correlation becomes 0, okay, at some lag. So according to this property, we actually shift one of the variables by the lag, which corresponding to 0 correlation. By doing this, then we guarantee the two sine wave, okay, or noisy sine wave will have no correlation, no causal relation. So in this way, we generate the surrogate data and train it, get a threshold value, then use that value to evaluate original data if there's any causal relationship. Anyway, so because introduction of the physics informed the causal relationship, and we have wide scope applications. For example, in a predictive modeling in a physics-based system, once you have physics information, you can use this approach. And the health and biomedical research, they have a lot of information, prior knowledge, expertise, know-how available, okay, can be included. And energy system optimization and also general engineering application, whenever you have any physical information, prior knowledge, you can include them in the analysis. Now, I'm going to talk about the two case studies. Okay, two case studies. They all come from real data. The first one is benchmark problem, okay, which Australian refinery separation unit. And for people who do not familiar with this separation or distillation column, I just briefly introduce it. So basically, for the separation or distillation column, what do we do is that we have feed, typically the crude oil, the oil, okay, per barrel. We talk about barrel oil with price changing every day. So oil come to this unit, okay. This unit basically heat up by some steam, heat up. Once it heat up, this crude oil will separate. The light component of crude oil will move to the top, okay. The top product will be lighter one, for example, gasoline, okay. The heavy one will be separated, move down to the bottom, for example, like diesel, for example. In this way, we separate light component from heavy component by this column. Okay. So in this particular process, we have 5 control loops, 5 control loops. Okay. Each control loop has PV, OP, meaning input and output. And so the first variable called AC1, which analyzes a composition of the top stream product quality, meaning that top stream product, how purity or top stream product, okay, called AC1 analyzer. And we also have the temperature of the column, okay, TC. And then we also have the pressure of the top product stream. That depends on the demand, how much demand of the gasoline, for example, downstream. also have the pressure of the bottom product, okay? And finally, we also have the steam flow rate, okay? And in fact, in this case, we know that the solution, because benchmark problem, the problem comes from FC1. So we want to, given the data, we were able to find this problem to troubleshoot the source of problem come from FC1. Now, obviously, first approach, we start from the original Granger analysis, okay, causal analysis. And you can see the map is pretty complicated, a lot of relationship as expected. Now, how we determine which variable may be the cause? So we can look at which variable, which point out to other variable most often, meaning that you can see arrow, the map, arrow pointed to other, all this arrow from this variable will point out to other variables. So that most likely to be the cause of the problem. So in this particular example, we can see the analyzer, the AC1, which is the top product, they actually point out to most other variables. So we may intend to think about, to consider this AC1 as a source of problem, which is not true. Also, the TC, the temperature, also point out to other variables most often. So we may get a solution that the AC1 is problem source or TC1 as problem source. Both are wrong, okay? So original analysis are wrong. Now, if you look at the right-hand side, we use sparse Granger causal area analysis, actually also wrong. It also indicates this AC1 to be the source of the problem. So both are not correct. Now, we actually, in this particular process, we have a lot of information we know. We have know-how, okay? We know some knowledge we know, okay? So for example, what do we know? So we know that when we heat up, when we add steam, okay, steam to heat up, of course the temperature is going to increase. So you know that's always a causal relation between flow rate, steam, and the temperature column, okay? And we also know that when temperature increase in the column and the more light product will flow to the top, it's going to affect the concentration or purity of the top stream product. So we can see the temperature column will affect AC1. So that we know the causal relationship. But what we also know that this AC1, which is product concentration, doesn't reverse affect the steam flow rate. Meaning that this causal cannot reverse, meaning the product steam purity not cause of the flow rate change of the steam. So we know that no causal relation from AC1 to flow rate, okay? We also know that this temperature change in the column going to heat up, change the composition of the top product steam, top stream product purity, but doesn't affect the pressure. Pressure depending on the downstream requirement. So there's no causal relation between TC1 and PC1. And finally, we know that the two pressures related to product, top product, bottom product, they have no relationship. They cannot have causal relation. So with 5 known causal relationship to be included, and we can come out the solution. So 5 unknowns, 5 known causal relation, and a list objective function. And we know here's the actual cause, and we see the result. Okay, so here result. You can see that the flow loop, one is the input, one output. They are causing to each other, the feedback, of course, they're causing to each other. But they point out to all other variables. So let's correctly identify that this FC1, so FC is the problem source. Okay, so let's correctly identify the issue of this loop. Okay, and finally, and quickly, I'm going to go through another case study, which is actual real industrial case study. So basically, this is the separation column, similar to the one which I mentioned earlier, but it's more general. So you can see in this case, you have distillation column, as I mentioned earlier, your absorption column, extraction column, absorption column, and the ion exchange membrane column. So a lot of application, this separation unit. Now, it's very important to industry, like physical, petrochemical industry, pharmaceutical, and food beverage, they all use separation process to produce a product. Now, the long-standing problem for the separation unit is called flooding. So what happened to flooding? So basically, as I mentioned earlier, we heat up this column, and then we separate, they're able to separate the light product to the top, the heavy one go to the bottom. The heavy one basically becomes liquid. The light one becomes steam, become the gas, will move to the upstream. But when you have too much steam coming to the flow up, it doesn't have enough ability to absorb it, to separate it. The steam going to condense in each tray, and going to flood it, going to flood the tray. When flooding occurs, it's very quickly. When flooding occurs, then the product stop, and they're going to produce off-gas specification. So this very common problem, very hard to solve. It's so quick happened. So we want to find the solution, meaning that predict it. We're able to predict it for a few minutes earlier. You're able to prevent it from happening. So that is what we're going to try. So this is a specific industrial process called the propanizer column. Okay. This column tries to separate and this propane from ethanol. So they separate in two different streams, as mentioned earlier. So propane would be main product, and on the top, and other heavy product in the bottom, and the separation process. So we want to know this flooding occurs very frequently, but cannot prevent it. So we want to predict it and prevent it from happening. So what we know that in this case, we do a causal analysis. So in this case, that's called indication called differential pressure variable. This variable indicates flooding. But this variable, when this variable start jumping up, the flooding already occur. So you cannot do anything else. So looking at this variable, more indication of flooding or not, but cannot use it for prediction. So we find the prediction of this variable. So what happens is that we have totally 16 process variables. We have data for a year and a sampling rate of 1 minute. And here's the flooding. So this differential pressure suddenly shoot up and the flooding occurs. The product stop, production stop. So we want to predict this shooting, this impulse jumping by other variables. So now this is a variable we have, 15 variables. So we do the causal analysis. Again, we tried original granular analysis, which doesn't work out. Sparse way, it doesn't work out. We have to include the physics information. So similar to the earliest example, we have some physics information available for this particular example, the process, and such as the reboiler, steam cost, and so on, the causal relation, we know it. So include it in the analysis. So then we find there are 4 different sources. Okay? So idea is that we want to find the source variable, which is away from the column, the distillation column. So we give enough lead time to predict the flooding is bound to happen or going to happen. So we find the 4 variables, which based on this causal map, 4 variables which feed flow rate, feed temperature, and reboiler stream, and the reflux. Where are they? So here what did they happen? So this is feed coming from earlier. So this gives advanced warning if we know, if we can monitor this variable. And there are 2 variables, feed and also reboiler and reflux. So these 4 variables which can lead to the flooding, they are causal relation. Now, once we know the 4 variables are source, then we can monitor these 4 variables by using PCA, typical PCA. With 4 variables, we compress them, find a feature, and to get the t-square, which can be utilized to determine, to monitor this flooding situation. So here's the training. Again, we need to train the threshold value to get a t-square test. Again, use historical data. We train given some fixed alarm rate and the false alarm rate. We find the threshold value will be 10.2. So this is going to be threshold value for future monitoring purpose. Now we have 4 events successfully predicted. So here are 4 events. So event 1, 2, so event 1 is for training. We don't this historical, we don't use it. But 2, 3, 4, 5 are the new event we want to predict. So this is immediate before the event occurs. So this dashed line means event occur. This is t-square test or monitor index. Okay. Here's threshold value. As far as cross threshold value, we're able to give alarm. Okay. So you can see all 4 events immediately before the flooding occur, we do have this indication. Now by calculating time, so event 1 get 18 minutes lead time, and so on, 30, a minimum of 20 minutes. We give sufficient time for operator to take action to prevent flooding from occurring. Anyway, so today we we discussed the causal relation, what the definition of historical overview. And we then introduced granular causality, the most fundamental one. Then we evolved to a sparse causality analysis, causal analysis. Then we introduced physically informed causal analysis. Then we talk about how to train the threshold value, which is important under this unusual solution. And finally, we have two effective industrial application results. Okay, I like to, this is a paper which summarizes the work presented here. And also, I like to acknowledge the support from NSERC and the University of Alberta. Thank you very much. I'm happy to answer questions you may have. Okay, thank you.
For questions, it's really very interesting to know that, yesterday we were speaking about the problem of data driving without physical information. He showed that the physics tell us a lot. The information is there and we have to use it the correct way in which we can use the information of a physical system with causality and correlation. And I open the discussion if there are some questions of the people,
I just want to address the comment about the physics information. So physics, and actually we have now with machine learning AI, and the people all come to the just database and learning from historical data learning. We forgot that we spent 4 years, 6 years learning our fundamental in chemical, electrical, mechanical. Somehow many people throw away of this knowledge and come to the machine learning only. So we're competing with computer science who are specialized in programming data analysis, abandon what we have. So physics will definitely useful for engineers like us to include it in the machine learning or AI type technique. This was just a quick comment about very often people ask about the physics information.
Some question? Oh, yes, here. But please come here, I think. Do we have a microphone there? Yes. Yeah, it's okay. It's open.
Bill, thank you very much for this very interesting talk. This really laid the foundation for this FDI. You got to know what is the physics behind it. I have a couple questions. One important thing is, we know, we said we know what we know. We know what we don't know. But there's a third one, is we don't know what we don't know, right? So when you look at these variables that you have uncertainties, it could be some other variables which we do not know it is there. Causes uncertainty. Do you have any way to capture this part?
Yeah, that's a very good question. A simple answer is no. Simple answer is no way to find it out. Now, this is also the reason for this causal analysis to be very contradictory, because for different people, different algorithm, different variable selection, you have different relationship. Just because exactly what you just mentioned, some variable are missing, you're not included, and of course the result will be different. Now, this is the, again, chicken egg problem. So if we have the physics information, so if we know the physics about the whole unit, then we are able to find all variables which may be related and be included. Then we start doing this so-called data-based approach. So again, let's bring back to physics. So I think the causal analysis, to ultimately get a reliable solution, we would have to start from the physics at the beginning, not start from data. So get the physics relation and find all these variables that may be causal related. Then we start data-driven, data-based. But within data-based, we still need to include the quantified relation between whatever we know, whatever we do not know. And so the question, whatever we do not know, we need to somehow include it. Okay. But again, it can still miss some of them. It's always open question here.
So you force this M12, M22 be very small. So basically you discount that impact, right? So it's physics inspired. But could that be this M1, M2, M22, they're not supposed to be 0 because there are some other factors, affect. So when you make these assumptions, you are not really address the real problem. I'm just thinking, because it says that the universe, in the universe is 80% is dark matter. We don't know. So how you force it to be small. So it's debatable, chicken egg. But it's very, very interesting work.
Yeah, and again, just for the question you mentioned, and I think that for granular cost analysis, and the result, I think is more on the direct, if all variables included, and then this M refer to the direct causal relation. So indirect one will be captured by, once indirect one, it captured by, because all variables included. So direct one has most coefficient number.
Okay.
So all number appear in the M matrix will be direct causal relation.
Okay. The second question is the distillation column you talk about. You have not considered the feed. The crude oil crude oil can be a different characteristics, different components, and so on. That can be the huge impact to all those 5 loops. Can you comment on that?
So we talk about the first case. Our second case, we do consider feed for the actual one. The first case, I think you refer to the first case, which is Australian benchmark problem. I think it what you are referring to for the, this refinery process. But for the refinery process, I know we do not have access to the feed data. So this is the benchmark problem, right? Benchmark problem. We only have data that provide to us. But you are right. If a feed can be included, then maybe even better result. But in this case, right, basically talk about this Australian case. Okay, sorry. So this one we do have feed, for the actual industrial application we have feed. And but first one, the benchmark problem. This one, okay. This one, and we don't have variable or feed. They only provide 5 variables. Okay. I think, only 5 variables are included in this particular case study. Yeah, the feed, I assume, for the data they have, the feed path pretty constant. So this is why, and this remaining variable, we are able to identify where's the source. Okay, but I think the feed, they don't provide the feed, I assume they are pretty constant value for it.
So this is a good example of you don't know what you don't know.
Right, yes, yeah. We do not know, but in this case, they know. The people, refinery people, they know, but they don't provide to us.
Okay, there are some questions. Yes, Professor B was there behind.
Yeah, so, coming from computer science, in the past we have worked on this notion of integral versus derivative causality, because say when you're expressing relations as integrals, right, which variable causes the other variable to occur becomes obvious, because in integral there is always a delay. So it relates to this idea you were talking about earlier, right? Derivative causality, of course, it's very hard to determine the causality. But what I was wondering is, what is the relationship between integral causality and your Granger causality?
You talk about integral causality?
Yeah.
Can you explain?
Because see, when we write out the relations for a physical process, right, you are usually writing out ODEs. And the way you solve the ODEs is by integration.
By integration.
Yeah, so you know which variable results in the next value and so on and so forth. But whenever you have an integrator, there's a delay, right?
So you talk about integrator will automatically indicate the causality, or?
We have done that in the past. We worked with this notion of bond graphs.
Okay.
Where if you look at bond graphs and look at the integrals, right, then you know that x causes y because y is an integral of x.
Okay. Yeah, I'm not aware of integral solution. It would be interesting to look at the integral. I would imagine integral will increase this effect because you are accumulating over time.
Yes.
And enhance the effect. which may give you even a stronger indication. But I also wondered if there's more bias, because in reality, the wearable often have sensor. In reality, or process often have instrumentation issue. So some bias in the sensor, which after integration, they can become huge numbers. I don't know if that can cause any problem or not, but yeah, that's true. Integration will increase the causal relationship. But I don't know how the physics information be included in the integration. I talk about solving differential equation or?
I mean, we're solving differential equations structurally. Right?
Okay.
You're writing it out as a graph, and therefore you're deriving the causal relation.
I see,
from
okay. So you talk about all from physics perspective. So
Yeah.
you have whole equation and the differential equation, you should integrate it, and then you can find the causal relation.
Yeah.
Okay.
And I was
Yeah.
wondering how that corresponds to Granger causality. Right? So I never worked with Granger before. So.
Yeah, I do not know. And the Granger causality analysis really come from database. So they do not, historically, they don't include any original ODE and type of equation. They're all purely from the data, building the AR model, then create this causal relation. But I guess when you solve this integration from first principle, eventually you come out to something similar, okay, which integrate result. Sure. And for Granger one, it's already integrated, almost integrated because it's wearable. There's no differential relation in there.
Exactly.
Okay.
Yeah. Thank you.
Thank you.
Yeah, please. Do you have the micro? Please, Marco, you are the co-chair.
So thank you for excellent talk. I have one interesting question. So many of these industrial processes and chemical processes, they have multiple operating modes, right? So one of the big challenges is to try to identify faults or diagnose faults during transitions between different operating modes, right? But some of these transition stages might violate some of the assumptions that you made in terms of stationarity. Have you thought of solutions to these problems by using causality analysis?
Yeah, and it's a good question. And actually, when Granger introduced this Granger causal analysis, all day, the modeling tool is very limited. And it really time series analysis with AR model and so on. So they assume stationary, assume linear relation. But nowadays, you look at literature, at least extend to the machine learning and the nonlinear. So Granger definition really doesn't say it must be linear. It's a solution because they're not able to solve nonlinear problem. So they use the linear solution. But definition just past X has effect on the future Y. If this occur, then that's Granger causal relation. That doesn't say they have to be linear. It's just in that time, they want to solve this problem. They have to find linear model first. But nowadays, no limitation. Multi-mode also has solution. Multi-mode, you can also include it for the multiple mode change. They have different relationship. So that also introduce complexity of causal, meaning that in this mode, there may be no causal relation. But go to other mode, there may be causal relation. The one with sun. So the person sees no light, and then he said the sun doesn't exist.
Yes.
But that same thing, so it is different mode. The day mode and night mode, the causal relation are not same.
Yeah, so basically we'll combine this idea of causal analysis with some more complex machine learning methods than principal component analysis.
Yes, yeah, actually they are quite popular now. Is they go back to machine learning and they try to use machine learning to get much more complicated causal relation. I think causal relation is very essential for detection, for diagnosis eventually.
Yes.
Yeah.
Thank you.
Yeah, thank you.
There are another question. Yeah, here we have some. Please, Marcos.
Yes, please correct me if I am not right. So I have an impression that you gave us a message. Please pay attention to qualitative fault diagnosis rather, or maybe instead, or parallel to qualitative fault diagnosis that is based on models. Can you discuss shortly this topic?
If you speak a little bit, could you repeat the last part of the question?
It's a balance. The problem is the balance between the qualitative rule-based diagnosis, diagnostics, and quantitative, of course.
I don't want to talk about fault detection in particular. I talk about this causal analysis. Maybe it's a limit to causal analysis because I talk about causal analysis. Now, the causal analysis, the problem itself is qualitative. A cause B, B cause C, and then qualitative. But we could not solve that the way. So, the way we solve it, we have to quantitative, meaning that we have to find the actual relation between A and B, and at least value from A. You can think about the strengths or causal strengths. So causal strength of A to B may be strong, may be weak. Sometimes you have small causal relation, sometimes strong causal relation. But again, so the solution is quantitative, but the answer is qualitative. So far, we don't say how strong causal relation. We only say A cause B. But you are right, and for the fault diagnosis, maybe this quantitative information can be utilized to enhance this so-called diagnosis reliability. Okay, so that's all my comment about causal, in the causal relation perspective. Yeah.
Thank you.
Thank you.
Another, please take the microphone. So there are some other questions in the audience. If this is not the case, then I will thank again to Professor Wang for this very nice talk and discussion. And we started in 20 minutes again. We have a break now.
This session, the title is Model Predictive and Reconfigurable Control. I know that some people are still coming back from the coffee break, but hopefully soon we will be ready to go. We are starting with the first talk, which is hierarchical fault-tolerant coverage control for autonomous aerial agent. It is by the group of Kios, and the speaker is Papayano Savas.
Thank you for the introduction, and good morning. So yeah, in this work I will present our work on hierarchical fault-tolerant control for autonomous agents. So the outline of this presentation is as follows. First, I will motivate this work and discuss a little bit the related work. Then I will summarize our contributions, discuss the proposed approach, talk a little bit about evaluation, and then I'll conclude this work. Basically, coverage planning is a very important task in autonomous systems, and this takes part in many application domains, including infrastructure inspection, automated maintenance, emergency response missions, and construction automation. So basically, coverage planning, what we are looking for is to find a trajectory which allows an autonomous agent, like a mobile robot, to cover or observe with a sensor every point within a specified region of interest. So in this case, what we need to do is basically guide this autonomous agent, find a trajectory that can cover all these blue points, and also control its sensor. So in our work, basically, we assume that the nominal control inputs of this agent are affected by random disturbances, and effectively the agent actually operates under, let's say, faulty controls, or and the idea is to design a trajectory that can accommodate these disturbances, and the agent can finish the mission. So okay, so basically this problem has been investigated in the literature. Just a brief overview. So initial works basically try by decompose the environment to a finite number of disjoint cells, and then they kind of utilize a path planning algorithm to traverse every cell in the environment. So subsequent works have investigated the coverage sweeping pattern, the sensor footprint size, and the cell traversal order. And recently, we have extensions to multiple agents and extensions to UAVs. So, however, existing works still focus on 20 environments, which they call terrain coverage, and basically utilize uncontrollable sensors. And this allows them to reduce the problem into a more like a path planning problem. So now, in terms of fault tolerance and robustness, stochastic, let's say, control approaches, basically mostly utilizing deterministic bounding disturbances, or they are based on linear Gaussian assumptions. Other works, fault-tolerant robust methods, basically accommodate nonlinear system dynamics, but often they presuppose still Gaussian disturbances. And in contrast, to handle non-Gaussian disturbances, we have scenario-based stochastic control methods. However, these methods are usually applicable for linear systems. Okay, so basically, in this work, we propose a hierarchical fault-tolerant coverage controller, which in its first stage generates an ideal coverage plan. This plan enables an autonomous agent to cover specific 3D points of interest. And in this stage, we formulate the problem as hybrid optimal control problem that optimizes the agent's mobility and camera control inputs for maximal coverage. And then subsequently, to handle stochastic disturbances affecting the nominal control inputs, we design a second stage fault-tolerant controller that integrates exact assertive propagation techniques, and we use mixed trigonometric polynomial moment propagation to enable the propagation of non-Gaussian disturbances through the agent nonlinear dynamics. And subsequently, we can design deterministic constraints based on the moments of the agents at certain states and enable robust missions. So, okay, so basically what we are doing here is we assume that we have a UAV agent that operates inside a bounded environment. the agent follows some dynamical model like, in this form. Here this is an example where the X, Y, Z and the psi is the agent state, U's are the control inputs, and then we have these terms here, the omega, that are random disturbances. And so this random vector here, which includes these random disturbances, we assume that these are actually random variables which can be from any kind of distribution. They can be non-Gaussian, they can be bounded or unbounded, but we assume that these random variables have finite moments. So then we also assume that our agent has a controllable camera, and we model the camera like a pyramid, and this basically this is the field of view of the agent, and which can be basically rotated using this kind of transformation with two rotation matrices. And the objective now is to basically cover the points on the surface area of some object of interest, which we first triangulate, and this results in the object surface area is decomposed in a number of facets. And what we want to do is to basically design trajectories that allows the agent to cover specific points, like this one, on the corresponding facets. Okay, so now essentially we have to solve this optimal control problem where given a sufficiently chosen planning horizon, we want to find the control inputs of the agent that minimize the sum objective function. Here is the control effort, and subject to the agent's dynamical model and some coverage constraints, where here basically this constraint, what we want to do is every point of interest must be included inside the convex hull of the agent's camera field of view during the emission. So this is what we want to solve. So because the agent dynamics now is stochastic, this constraint is not valid. This is a deterministic constraint, and essentially we want to solve, want to impose something like that. So basically ensure coverage with certain probability 1 minus epsilon. So we want to solve this problem. And the idea here is to tackle this problem, we basically work in a hierarchical approach, where stage 1, we design an ideal plan, an ideal coverage plan without noise, and then this plan is taken by the second controller and makes sure that given the noise, accommodates this noise into the emission, so that the agent can have the result that we want. So, okay, so essentially the first stage, which is basically an MPC controller, what we do is that we devise a plan that can pass through a series of regions of interest that are associated with each point of interest. So these, let's say, these points of these regions of interest are called as K. So you have K of those, and we basically design an MPC as a mixed integrated quadratic program to find, let's say, an ideal trajectory that allows the agent to pass from these spheres and rotate the camera accordingly so that it covers the specific point. So here we have we do that by we have high-level dynamics, so not the original dynamics, this is noise-free dynamics. We have a constraint that basically indicates using a binary variable whether the agent resides inside some region of interest at some point in the future, inside the planning horizon. We have a constraint here that indicates that some region of interest, like some of these spheres, is not visited more than once inside the planning horizon. Then we use a memory term here, VK, which basically allows us to to discourage duplication of effort, so that inside the mission, we don't visit, don't go back and forth visiting areas that have been visited in the past. And then we have here the camera control, where basically we choose the angles that will result in coverage of a specific point. And then finally, using a binary variable here, we use this to activate it when some point of interest is actually inside the agent's field of view at some future time step. And then we combine these two into a final binary variable that we basically include in the objective, so that the agent actually is guided through these spheres. So and cover the actual points. So okay, so now once we have this reference plan, we utilize the second controller, and this controller will make sure that it can robustly guide the agent to the desired direction. So, and the main result, we built it on lemma 1, which basically says that if you have a random variable x with a characteristic function phi, then for a given triplet of integers and the scaling factor, we can basically compute the mixed trigonometric polynomial moment of order A, like in this form. So basically, we can compute the moments of this random variable when it's in this form using this formula. So in other words, we can exactly compute and propagate the moments of the system through time if they are in a mixed trigonometric polynomial transformation using this. So now, using this lemma, what we are doing is that we use kind of trigonometry to transform the original dynamics into an augmented form. So we have an augmented state here, and basically these dynamics here become in an augmented representation shown here, which is, okay, it's linear in terms of the augmented state, but what allows us to do is to use this let's say, uncertainty propagation technique, and we can propagate the tech expectation here, and we can compute moment state dynamics. So we can propagate through time the moments, all moments of our system in a recursive fashion. And given that, basically now we can use a probability theory and find, let's say, a probability inequality that we can use to bound some desired quantity. So if we say that here we want to have if D is the distance between the agent and the center of the sphere, and the SR is the radius of the sphere, we want to basically compute that the agent is outside the region of interest with probability at most epsilon. So we want to impose a constraint like this. So, okay, so in this work, if we define Fk like shown here, we use basically the VP inequality, and we derive an upper bound on this probability. And this upper bound here is actually composed of the variance and the expectation of our desired quantity. And this decomposes, this can be computed using the moments of our system from the augmented state. So to compute this, we actually need the first 4 moments. And essentially, our controller, our stage 2 controller, becomes this program. So we solve this program. We find the control inputs that minimize some objective function. Subject to here is the moment propagation, the moment state dynamics. And we guide this bound using our desired threshold. So now we have a deterministic constraints on the moments of the system at certain states, and we can robustly guide the agent where we want with probability at least 1 minus epsilon. And basically, this is kind of a high-level overview of this technique. Here is just an illustration that you have this object of interest here. The objective is to cover these points. This shows the associated regions of interest, and this is the top-down view. So then, this is the result of the stage 1 controller, where we devise this plan, and we control the camera to target these points. And this is it's an MPC, so it's like a rolling horizon operation, still in top-down. And then this plan is taken by the stage 2 controller, and what it does allows us to accommodate the disturbances. So here, for instance, in this simulation scenario, we say that this, let's say, disturbance here, omega, the horizontal velocity is a beta distribution with parameters 1 and 3. The vertical velocity is Gaussian, and the yaw rate is from uniform. So we have 3 different noises. One is unbounded. We have a bounded distribution, and this technique allows us to take all this together and robustly guide the agent inside these regions of interest. So we run a Monte Carlo simulation and for different confidence levels, and we have verified that this works. Okay, there's some. It's not the. There's some issues of conservativeness here, but given that we mix a lot of different distributions into this technique, I mean, sometimes it can be a good choice. So to summarize, we have introduced a 2-stage hierarchical fault-tolerant coverage controller for autonomous systems to cover 3 points of interest. So in the first stage, we formulate the hybrid optimal control problem. So we optimize the UAV's mobility and camera control inputs for maximal coverage. And the second stage, we employ a mixed trigonometric polynomial moment propagation to generate fault-tolerant coverage trajectories by accommodating non-Gaussian disturbances. We can propagate it through time. So in the future, we plan to integrate use this technique for non-Gaussian fault-tolerant camera and gimbal control and study extensions to multiple agents. Thank you.
From the audience? Yes.
Thank you for the interesting presentation. One quick question regarding the run times of the algorithms. What is the runtime of each algorithm, and if you run them, if they are possible to run online together, or what is the?
Yeah. So so stage 1 can run in real time. So the problem with stage 2 controller is because you're actually solving a non-linear and probably non-convex problem. Then depends, how you implement it. If you have some insights on your problem, so you can optimize it. So the general case is that it's not automatic real time because you solve a non-linear, non-convex problem. But if you have some insights on the problem that you're solving, you can basically customize your solver to make this happen in real time.
But the problem is like non-linear, so that you cannot use convex optimization, for example.
Yeah, if you have some, so if you know the structure of the problem, you can use some techniques to convexify or, guide the solution to part of the space that you want to explore more. or apply different techniques, some heuristic, some search, and some, but in the general case, it needs some effort to run, to make it in real time.
Okay, thank you very much.
Thank you. Do we have another question? Then let's thank the speaker again. And we can go on with the second presentation. Okay, so the second presentation is enhancing fault diagnosis in process industries with the internal variables of model predictive control. And the speaker is the Dr. Abdul Rahim. Thank you.
Thank you very much. Good morning to everyone. I'm Abdul Diallo, PhD student, and I will present a work done with my supervisors. And my project thesis is a collaboration between Arts et Métiers, ArcelorMittal, and the French region Grand Est. So the work is done in the context of process industries, which transform and process bulk of material according to a recipe or a formula. They are characterized by complex and integrated operations, and they require a sophisticated process monitoring system. And we may find in those monitoring systems at least one of the following elements. The first one is soft sensors that can predict, for instance, the quality of the product, because in process industries, generally the quality of the product cannot be measured online, so we need a soft sensor to estimate it in real time. The second component is a model predictive control that will optimize the operating conditions based on the inputs, the process characteristic, and also to meet the desired quality. And finally, we may find a fault diagnosis system that will detect fault and to isolate them. And this can be achieved through a knowledge-based method that whose accuracy decreases as the complexity and the size of the process increase, or analytical redundancy model, which are very accurate, but their use in the industrial context is limited by the complexity of the process modelization. And finally, we have data-driven methods that have attracted a lot of interest in recent years, but their use in the industrial reality is challenged by the nature of the data that we can find. So in this work, we are mainly focused on the last component, fault diagnosis, but we will use and we will rely on the first two components. So in process industry, the traditional controller is replaced by a model predictive control that will take as an input an optimization problem and then compute the value of the manipulated variable, and at the same time estimate some state variable. Some of those state variables can be measured through sensors, but the others cannot be, but they have a physical meaning. They cannot be measured through sensors due to economical reasons or technological reasons. So in this work, we want to assess whether or not using those internal variables with data-driven method will enhance the fault diagnosis performances. But one of the main problems is those internal variables cannot be, are often not stored in industrial databases. So a first step will be to extract them from the MPC logs. And we intend to assess this proposition in the context of industry where the data available for fault diagnosis are in two cases. In the first one, we have only unlabeled data, but we may extract some fault-free data with some effort, whereas in the second case, the data are labeled but greatly imbalanced with great amount of fault-free sample, but only a few samples in each of the faulty classes. So, for instance, training a classifier in this context will not lead to good detection and isolation results. That's why in this work we used a reconstruction method that mainly use fault-free data in their training phase, and their training process comprises four main steps. The first one is to train a reduction dimensionality model, and then to reconstruct the data from that reduced space through like a principal component analysis and independent component analysis or an autoencoder. After that, to choose a detection index, whether in the reduced space or in the original space, and then to set the limit of that detection index through statistical tests or kernel density estimation, for instance. And finally, to choose the isolation strategy that can be done, for instance, by contribution plots, MIT decomposition, and other methods. So, in this study, we first extracted the internal variable from MPC logs, and then we merged them with the plant measurements in order to train those reconstruction methods. And in order to evaluate the proposition, we use it to detect and diagnose fault in a hot dip galvanizing line, but we will mainly focus on the annealing furnace, where the mechanical properties of the steel are improved, but those mechanical properties cannot be measured online. And we will compare mainly, or we have already compared mainly three methods. The first one is a PCA and a kernel ICA and an autoencoder finally. And we will take into account two scenarios. In the first one, we will use only plant measurement, whereas in the second scenario, we will add to those plant measurement internal variable extracted from the MPC logs. And we were interested by 6 faults. The two first will happen before the galvanizing line, but have a strong impact on the product during the galvanization. But they are very difficult to detect online by the operator. Whereas the 4 remaining faults happen on the annealing furnace. And we used the model predictive control that have already been deployed on the line, and a model of the line to generate the data, then to extract the data from the internal variable from the logs of the MPC. And around 35,000 fault-free samples are used to train the compared method. Whereas in the test sets, we have only around 9,000 fault-free samples, but we have for each fault class around 44,000 samples to evaluate and to assess the methods. So we can see in this figure that based on the average detection rate, that incorporating those internal variables enhance the performances of the compared method. And you can also see that the autoencoder gave the best results, whereas the PCA was worst. Maybe because the process is non-linear, and the relations in the data cannot be well captured by this linear model, the PCA. And finally, we used contribution plots on the reconstruction generated by the autoencoder to try to isolate the fault. So we can see that, see in this figure, for instance, for a sample from the fault-free data, all the variables have a low contribution, at least if we compare it to samples from the fault 1 and fault 2, where we can see that KC1, the first variable, has the strongest contribution. And also we can rely on the sign of that contribution to identify which one between fault 1 and fault 2 are happening on the line in real time. But this is only for one samples. We can ask whether it is consistent for all the test data, and also for the other faults, what is the state of this KC1 variable, whether, because if it still has the strongest contribution or even a strong contribution, we cannot rely on it to isolate fault 1 and fault 2. That's why we depicted the contribution of the distribution of the contribution of KC1 for all the fault and the fault-free data. And we can see that we can separate those contributions by two red lines. So we can rely on this variable, on KC1, to isolate fault 1 and fault 2. And also we can rely on the sign of that contribution to isolate fault 1 to fault 2. Similarly, for each of the studied faults, there is a couple of variables that have a strong contribution in the presence of that fault, and a very lower contribution in the absence of that fault. So to summarize, we have seen that that incorporating internal variable estimated by the MPC can enhance the performances of reconstruction method. And for this study, the autoencoder outperformed the kernel ICA and the PCA, and contribution plots are used to isolate the fault. For our next works, we intend to focus mainly on techniques in order to quantify the uncertainty of the machine learning model, in order to give to the operator, to the engineer, more reliable prediction and also more informative information for decision making. Thank you for your attention.
Thank you. Yes, we have a question.
Thanks for the nice presentation. Just curiosity, did you make any comparison between your method and other method? For example, you mentioned that one obstacle could be the fact that you have unbalanced data, but today we have a quite a good set of techniques to cope with unbalanced data that work pretty well, good. So I'm just curious if you create any comparison between traditional method to balance or cope with unbalanced data and your result.
Thank you for your question. In this study, we have taken only this method, and we didn't want to augment the amount of faulty classes, for instance, in order to not decalibrate the prediction of the calibration of the machine learning model, because some techniques that deals with imbalanced learning, they decalibrate or the prediction of machine learning model. But it will be, yes, a good things to do to compare those traditional methods and what we propose in this work.
Thank you. We have time for another question. Then I will ask a question, if you don't mind. If you can go back to slide 14, I would like to understand, you were defining this threshold, the red lines. So how do you define this? How do you, how are they set? Is there a methodology behind it?
No, because the the objective of this figure was to see whether the distribution of the contribution of fault 1 and fault 2, they do not overlap with the other distributions. So these two red lines, it's only to see because for people that there is no real overlap. But we just saw the distribution and we defined two real red lines, and it was suggested by reviewers of the paper in order to give more visual representation.
Can this be something case sensitive or application dependent, or do you think that there could be some way to prove it?
Yeah, thank you.
I'm just curious.
Yeah, exactly. Yeah, contribution plots are not a very effective method for all the cases. So because it doesn't have a statistical guarantee that it will work so it is possible for some other data or for some other process. We will have smearing effect, and we will have many variables that will contribute in all the faults, so we cannot rely on the contribution plot to isolate the fault, so we have to try other methods for that.
Okay, thank you. Thank you. Is there any other question from the audience? No? So let's thank the speaker again. Yes. Yeah. Yeah. For the third presentation, we have a video, so I'm going to prepare it.
Okay, hello everyone. It's
Sorry, just a second. Okay, so the third presentation is resilience countermeasures for network control systems under denial of service scenarios by Franze Giuseppe, Lucia Walter, and Tedesco Francesco. And yeah, we have the video.
Hello everyone, it's Francesco Tedesco speaking from University of Calabria, and I'm going to present this work entitled Resilience Countermeasures for Network Control Systems Under Denial of Service. So here just some information about the motivations and aims behind this work. So the main aim of this work is to design a resilience control framework based on MPC arguments for cyber physical systems that are subject to cyber attacks. The core of this work is based on the perturbation analysis arguments. The main benefits are that the attack detection mechanism does not require any authentication mechanism, and the proposed solution does not need to periodically refresh the communication network. This is one of the main drawbacks of these usually for these control frameworks. And we are able to postpone a refresh of the communication networks, or in principle we are also able to avoid the communication, the refresh of the communication. Well, let's go to the problem formulation. So this is the main the main scheme here. So we have this plant that is described by a linear time variant discrete time model subject to a certain bounded disturbance. The plant is also subject to some input and state constraints. And you can see that the plant is controlled by this controller that I'm going to describe next slide. And this is a remote controller, so there is a communication network that is subject to some bounded delays. Okay. Let's see the controller, we assume. So this is a network controller, so I call this NCS MPC, and actually this is a controller is based on this paper. Okay, so basically this is a sort of MPC, so we assume that there is a target region T0 that is related to a feedback control law. So this feedback control law is able to maintain this state, even delay the state within this set. The idea is to alert this set by computing a sequence of robust controllable sets in this way. So here you see this set is enlarged by means of these families of sets. And the control problem is that starting from certain initial conditions, this controller is able to steer the state in the target region. So this is the optimization problem that is solved at each time instant. So first the state is the current set is detected, and then at each time instant the control problem is to make to jump the state into the successor set. Okay, when the state reaches the target regions, then the feedback law is applied. The important thing here is that this computed input can be applied for at most bar tau steps, where this bar tau, so it becomes the maximum allowable transmission interval in the network. If the conveyed signals, if the network is characterized by the delays that are greater than this quantity, then the controller is not able to stabilize the plant. And in fact, we assume that there is possible cyber attacks for these plants are denial of service attack that are aimed to make this quantity, so the communication delays, greater enough to make the closed loop system unstable. So we assume that there are attacks on both communication channel, on both controller to actuator channel and sensor to controller channel. And in both cases, there are these attack scenarios. So we issue the data loss when this quantity is greater than bar tau, and the feedback loss when this quantity is greater than bar tau. So the problem we want to solve is to extend this original control structure, that is the NCS MPC, in order to maintain the closed loop system uniformly ultimate bounded despite an admissible data feedback loss, so despite any cyber denial of service cyber attacks. This is the proposed solution. Actually, you see that we provide the original controller with a detector, and there's a feasibility check block that I want to describe next slides. And we have also modified these the plant side blocks. You see, here now we have these sort of smart actuators that is able to perform some computations, and it is also endowed with the detector and this block that is the perturb MPC. So this block, this perturb MPC, is related to this problem. So given a solution for the controller that is NCS MPC, that we already seen in previous slides, So this is the solution that, that is computed at each time system. The problem is that, is it possible to compute a new solution by exploiting only the existing solution and a perturbation of the original state? So this is an original solution. If we, for this state, if we perturb this state in this way, we can we compute a new solution? Yes, it is possible, and the solution is described in this paper here from by these guys, Gemi and San and Kolmanowski. And actually, it is possible to compute a new solution that is actually a perturbation of initial solution, where this perturbation is computed by exploiting perturbation analysis arguments. And the new solution is based on the original solution you see, and the perturbation that in this case, for our work, is computed as xt plus 1 minus xt. Okay, so this is a one-step state difference. These quantities are available on the plant sites. Moreover, in order to compute the solution, we need to provide the perturbed MPC with the Lagrange multipliers of the original control problem. So we can exploit these perturbed MPC in our framework in order to make this framework resilient. In particular, we have to observe that the original solution, the original input you see that is provided by the original controller is designed to steer the state from a certain set to the successor set. The new solution, the perturbed solution, is not able to perform this operation here, but it is able to maintain the new state into a certain set, into a bounded set. So the new solution, the perturbed solution, is not able to make the system asymptotically stable, but it is able to maintain the system stable. Okay, so it is good for us. We lose for performance, but we avoid to make the system unstable when the cyber attack is ongoing. Another important aspect is that on the plant side, the structure of the original controller, of the remote controller, is unknown, because the only information conveyed to the perturbed PC are these controller, the control input and the Lagrange multiplier. Okay, so the privacy of the original remote controller is preserved. Well, here are some operations we perform. First, on the control side, so we provide the controller with the detector that actually check the timestamp of the signals coming from the sensor, from the state, and outputs these attack, no attack flags. And this is a feasibility check. Actually, this block check if the state is within a certain set. That is, this is the set related to the controllable set at the time when the last attack has been revealed. If the state is not within this set, it means that something went wrong, and the system cannot be maintained. The state system cannot be maintained in this set, and maybe the stability is lost. So we have to refresh the network and establish new connections with the plant. Okay, here the online operations in this case, when no attack is ongoing, so this is the no attack mode, simply the controller convey its control inputs to the smart actuator along with the Lagrange multiplier needed for the perturbed MPC. In the attack mode, the controller doesn't convey any information here. And in this case, if the feasibility check outputs invisible flags, then the network is fresh. Otherwise, if the detector is outputs a no attack label and the feasibility check is okay, then we jump to the no attack mode. On the plant side, we have also a detector that works as the previous one, but in this case, the input is the timestamp on the input signals is checked. When an attack is detected, this variable this is a counter is set in this way. And otherwise, if there is no attack, simply the UT signal coming from the original controller is applied to the plant. So in the attack mode, these counters is used in order to apply the input conveyed by the controller can be applied for a certain amount of times. When this input cannot be no more applied and we have no more information from the original controller, it means that the attack is still ongoing, then we start to compute the perturbed solution by means of the perturbed MPC. So in this situation, the system can work by applying these new perturbed solutions until the attack is finishes, or until a communication network refresh is carried out. Well, here a brief simulation example. We are dealing with a two-area power system and we want to solve a standard low frequency problem. So in each area we want that the deviation from the frequency deviation is steered to zero in order to match the demanded power and the produced power on each area. So there are some constraints in the plant, constraint related to the frequency deviation, to the exchange of the power between the two areas, and the produced power. We assume also that the MATI is at 2 seconds. Well, this is the plot of the load request in area 1, and we assume that there are two cyber attacks. The first one, this one, is on the controller to actuator channel. The second one is the sensor to actuator channel. It is you see it is a longer. So we compare the proposed control framework with a non-resilient control approach. Basically, that is the control approach, the original controller I show you, without all these stuff related to perturbed MPC, smart actuator, and detector, and so on. You see that the blue lines here in the plots are related to the non-resilient MPC, and you see that constraints are violated during the second attack, actually, also here during the first attack. Otherwise, in the case of our approach, I zoom here. Here you see that you look at the green line. So this is the solution computed by means of the perturbed MPC that is used during the attack. And you see that here the effect we obtain on the frequency deviation here is that the frequency deviation during the attack is not steered to zero. So basically the original control problem cannot be solved, but the system is maintained safe, maintained stable, okay, during the attack. When the attack is complete, the normal mode is ongoing, and again the frequency deviation can be steered to zero, and so that's all. Let's go to conclusion. So in this paper, a model predict control framework ensuring the safety of the constrained cyber physical system has been developed. Here the core of the process, the framework is based on a perturbation analysis, and it is mainly used these arguments for avoid network refresh procedures. When denial of service attacks are ongoing. A numerical simulation on a two-area power system benchmark subject to replay attacks has been used to show the effectiveness of the approach. Thank you and bye-bye.
We thanks the author, but anyway, we can say thank you very much, and we're going to start now with the number 4 presentation is the private press.
You want to wait 2 minutes?
Yeah, could you change these slides there to start your presentation? I think we need only to stop here with escape. Okay, let's go. Okay, then I introduce the 4th presentation. The name of the presentation is Privacy Preserving Approximated Optimal Control of Pasteurization Unit using homomorphic encryption, and the presenter is Frances Giuseppe.
Diana.
You are the Diana?
Yeah.
The Diana, how do you pronounce your name? Surak?
Zurkova.
Okay, thank you.
Okay, I will introduce myself.
Okay, we are on time to start. Maybe we can wait a little bit because we are a little bit early with
2 minutes.
with the other. Yeah.
Okay. Oh, okay. So thank you everyone for attending. Thank you for the introduction. But to introduce myself once again, my name is Diana Zurkova, and closer. Yeah, sorry. So my name is Diana Zurkova, and I am PhD student at Slovak University of Technology. And today I would like to tell you a little bit more about the research that me and my research group are focused on. We are focusing on privacy preserving process control, and right now I will tell you a little bit more about it. So I think, is it not working? I think we can all agree that in this day and age we are living in a highly data-driven era. Every day, every minute, every second, there are huge volumes of data that are being either compared to something, evaluated over with, or used in a bunch of different analyses. And majority of this is happening within the cloud environment. And to highlight three more interesting fields that this analysis are happening in, I would highlight electronic voting systems, medical analysis that usually use highly sensitive private data, and last but not least, and the one that we are the most interested in, process control. Now, let's discuss some real-life example. Let's consider we have industrial plant, and that this plant is outsourcing its control system, and this is happening within the cloud. In this scenario, we are having data that is highly sensitive and is being transferred. Namely, the process data itself that is being collected within the plant and sent to the cloud, and the control action that is being sent back. In this scenario, this is vulnerable to arguably two types of attacks. The first one being malicious attack that usually wants to either cause some accident or to stop the production in total. And the other one being some kind of industrial espionage that wants to steal some know-how from the production. This is, of course, already protected by standard types of encryption during the transfer. But when we get to the cloud, we come to the problem of privacy vacuum. Because if this data is about to be evaluated in some way, it needs to be decrypted. Therefore, the cloud right now is the target of the attack. Or the cloud itself could be malicious in some way and could try to siphon this data. And this is where the homomorphic encryption comes into play as a solution. Now, when it comes to the homomorphic encryption and process control, it's not a foreign concept. There are already multiple studies done. Mainly when it comes to the older standard types of crypto systems that are usually applied.
I have to move a little bit down, maybe you can see better because
Okay.
I don't know, it is on with me because
Should I talk louder then?
I think it's, how are you sure that it's on? Because it's really very, can you improve this? You are going to change the microphone maybe?
Should I come closer?
For that.
Okay, you speak near the microphone.
Okay, sorry. So, as I said before, there are already some studies done. When it comes to the older types of crypto system, such as PyJ crypto system, those are usually used for lower types of control setups, such as PNID, for example. But if you want to do some higher type of control, we need to use more modern crypto systems. The most notable one, I would argue, is CKKS. This is actually the one that we are using in our setup. And this type of crypto system is rather attractive for process control applications, namely because it operates with real numbers, and it also allows for basic linear algebra to be carried over the ciphertext. And this specific crypto system belongs to something what we call level type of crypto systems, meaning that we have only limited predetermined number of levels within the algebraic circuit that we are able to send our encrypted data through. But let's actually talk about what the homomorphic encryption is. It's a special type of encryption that allows us to carry out operations over the data that is encrypted without any need for decryption, which, as you can probably imagine, isn't really an easy task, and therefore we are facing some challenges. The first one being that we only have limited types of operations. Depending on the crypto systems, we are either able to do addition, multiplication, or both of them. For CKKs, we can do both multiplication and addition. Another problem is the one that I mentioned before. It's multiplicative depth, which basically means how many consecutive multiplicative operations we are able to carry out over the ciphertext. And naturally, this encryption is usually more tanky and more computationally complex compared to the standard one, which usually comes hand in hand with more memory demands. So far I told you what we are trying to solve and what's our way to solve it. But let's talk in more detail how we actually done it. So we wanted to implement this thing to the pasteurization unit. At the beginning we took our typical control scheme where on the private side we have our general process, and this process outsources its control to the cloud, where the controller is being evaluated. In our scenario, we are using the pasteurization unit, which you can see over here, where on the left you can see the general flow scheme, what's happening in there. Basically we have 3-stage heat exchanger, and our main focus is on the holding tube, where in front and behind it we are measuring the temperatures, and we are also monitoring the temperature within the heating tank. And these are basically our 3 states that we are measuring, and our control inputs are the power for the heat pump and for the feed pump. And our, of course, general goal is to provide stable production. Now, as I said before, or as you can logically think about, is that this process has multiple inputs and multiple outputs, and we also want to keep our states and control inputs within some constraints that naturally come from like the physical features of the device. Therefore, naturally, the controller that comes into the mind that is suitable for this is MPC. Where we take our state measurements, we send it to MPC, and this calculates the control inputs, which are the PAM commands, and the whole thing continues. But the problem is that as of right now, when it comes to the current stage of research within a homomorphic encryption community, there isn't really an effective way to apply it. So we need to improvise. But let's talk first how our general optimization problem looks. We have our states, our control inputs, and our slug variables that are our optimized variables. And we want to provide a homomorphically encrypted version. This is challenging because when we look at the MPC and homomorphic encryption, we have three areas that it kind of clashes. The first problem is that MPC requires complex operations, and as I said before, we only have addition and multiplication.
Wait a little bit, I think it's something. Oh no, take this microphone, let's go to this. No, it doesn't work this. The battery maybe is empty or something like that. It's a phone.
That better.
It's a battery. So
Okay,
simple.
thank you. Okay, so sorry about the problems. Hopefully you can hear me now. So another problem is the nature of MPC, that it has iterative algorithms, and this is the main problem in homomorphic encryption, that we are limited when it comes to the consecutive multiplications over ciphertext. And last but not least, of course, MPC usually has some kind of tolerance as a stopping criterion, and we cannot do comparisons over ciphertext. So knowing all of this, it's safe to say that we don't have a straightforward way to implement homomorphically encrypted MPC, but of course there are ways to go around it. And one way to solve this is to use neural network, since it's more suitable within a homomorphically encrypted environment. But this, of course, comes with another set of challenges. The main one being that when we have neural networks, we usually have standard activation functions, which you can see over here, hyperbolic tangents, sigmoid, ReLU, etc. But these ones aren't applicable within our homomorphically encrypted environment. Therefore, we started to look into other ways to implement this. And we found out that it's a good solution to use polynomial approximations of these functions. And when we analyzed it, we found out that the polynomial approximation of hyperbolic tangent was the most suitable one for us. Oh, sorry. Here we have how it basically fits. We decided to go for 5th-degree polynomial, and compared to the original activation function, I would say it provided rather satisfactory performance. So we took these activation functions, we built a neural network with it, and then we decided to take our states, we quantized them. We ended up with 125,000 combinations of our free states, which are temperatures. We evaluated the MPC with them within MATLAB, and we generated the control inputs. And this set of data was then taken, split into 80% for training, 20% for testing, and then in Python we trained our neural network within a Keras deep learning API using Adam optimizer. And to actually test how well our MPC mimics the behavior of MPC, we set up some simulation where we started from arbitrary sets of states, and our goal was of course to control into the steady states. And to highlight this behavior, we also introduced two errors to the input, where basically the first one just simulates a complete shutdown of the pump, and the second one simulates override that basically sends power to the pump to 100%. And in both of these cases, MPC performed nicely, of course, but when we compare it to neural network, we see that it also provides really satisfactory mimicking behavior. We also evaluated the actual numbers, but as you can see from trends and the values itself, the discrepancies are nearly negligible, and they are of course to be expected because of approximative nature of the neural network itself. So we so far ran this within a simulation, and since we saw that it working, of course the next step was to actually apply it to the physical device. And what's happening here, we started the pasteurization unit, we take the state measurements, we encrypt them, we send this encrypted data to the cloud side, where within non-encrypted neural network this data is being evaluated. The encrypted control inputs are then sent back to the user side, and only here on the private user domain, here's the first and only decryption that happens, and then these control inputs are sent back to the device, and the whole thing loops around. Here I have in more detail what is actually happening within our neural network, or what's actually happening when we are evaluating our encrypted control law. At the beginning, we have our encrypted states that enter our neural network that has two hidden layers. Here you can see our polynomial approximations that are used as activation functions. And basically, the first layer has 50 neurons, the second one has 30, and the last one is just basic dot product. But this is how we evaluate our encrypted control inputs, and in total this consumes nine levels of multiplicative depth. Here are the actual results from the device, where we compare the MPC, the neural network, and the neural network that works with encrypted data. And as you can see, in all three cases, we are getting comparable results, with, of course, some kind of discrepancies, mainly because of approximative nature of the neural network, and of course with noise that naturally occurs when we are measuring some real-life data. And just to give you a general idea how big the data is that we are working with, here I have a table of the keys that we are working with for this particular setup, where we are working with the data that is ranging from 1 megabyte to half a gigabyte. And to test more how practical or how applicable in real life this setup is, we set up, let's say, benchmark test, where we took two virtual machines and we basically simulated that one of them is the process, the other one is the outsourced control that sits somewhere on the cloud, and they are communicating within the network using a typical HTTP communication protocol, and all the data is in hexadecimal form. And I would split this into two parts, the first one being the typical encryption, the typical handshake that happens within any type of encryption, which usually takes the longest, and this is exactly because if you remember the key sizes that we are working with, these are the ones that we need to serialize and deserialize, etc. But this only happens once at the beginning, so it shouldn't be an issue. Sorry. And this is the one that actually runs within the loop with all the sizes and times for the states and ciphertext and stuff like that. And this is important part because if we want to move forward with implementation, we need to consider stuff like this, how much the whole thing actually takes, because if we are within like industrial scenario, sometimes the network itself isn't performing that well and stuff like that, so this needs to be considered as well. And sorry, to conclude, we first looked into activation functions that are used or that are suitable for homomorphic encryption applications. We found out that fifth polynomial one is the one that performs the best in our application. We took that and we applied it first into simulation. We tested how it behaves. When we were satisfied with the results, we then applied it to the actual device. And we found out that even though we had to go through various challenges, and the whole thing is much more complicated than the standard encryption, we are still able to achieve very good performance. And what I want you to take from this this presentation is that maybe not in 10 years, but maybe in 20, maybe even longer, depends on the research, but I truly believe that this is going to be a future when it comes to the privacy preserving encryption. And it's going to be widely used, not even only in process control, but in day-to-day life. And that's it from me. Thank you for your attention, and I'm ready for your questions. Yeah, we have a question already.
Yeah, okay, thank you very much, and sorry for the disturbance, but it's a fall usually, you know. Okay, there are some questions here. He will have one. Please come here. Oh.
Hello, thank you for your presentation. Very nice, the work. But similar for the previous presentation in the field of cyber attacks in industrial processes, I have many comments. The first one is that really is no common that in the industry you find the controller in the cloud. Yeah. Because the controller is inside in the plant. And why? Because the time responding to the net, you can't control which time in process that is really, the reality is high in the industrial process. Then, okay, and the previous, always say some and cyber attack is someone else attack the net and put information. In the other guy expose the lies in the measurements, but sometimes the attacks are change the values or change some other things. But it's from the cloud, the hackers go to the servers, and from the servers go to the controllers. Then it is the field for attack, no the actuator to the controller, neither sensor to the controller. In this field it's a bus in the field, you can, because this field bus, Modbus, or another Profibus, these devices on RS485, that is a field bus that don't have access to Ethernet, in the layer of, don't have the layer of net, ni transport, then it's no access to internet, don't have IP direction, no sensor have direct IP direction. That is impossible attacks from outside. Then is my comment. Furthermore, maybe you know that the International Association of Automation and the International Electrotechnical Commission has a series, the 62443, a series of norms on cybersecurity in industrial processes. Then they establishes all the requirements and all the need for protect the process for these attacks. Then it's important to analyze all these norms and which is the probability that will exist these attacks and how we can prevent it. For the encryption, it's nice, and maybe the function hash is another function that can be used for encrypt the information, and this is another topic for the cybersecurity. But this is my comment. Thank you for your presentation, and all right.
Okay, thank you for your comment. I would argue that it's a very valid one, of course. But maybe I didn't paint the picture the right way, because this was just general example that I wanted to show the problematics of course, majority of stuff is local when it comes to the industrial control. I don't argue with that at all. And we don't even focus on the safety part, but more of the privacy preserving part. Because the safety part is already resolved. But we still have this privacy vacuum that is happening within the cloud. And maybe industry isn't the best example for this, but maybe in the future when you have an industry becomes more open-minded when it comes to the higher types of control, like MPC, yes. When it's going to become more common, I would say maybe in the future there is a space for cloud-based control in there as well. But there are other fields where we already have that. And this is where this is important. But yeah, of course, all the other safety stuff you are 100% right on. But thank you.
There are other questions, other comments. Oh, here we have one, and the other. Oh, wait.
Thank you for your nice presentation. I have two questions about your work. From my understanding, it takes time to encrypt and to decrypt the data. So my first question would be, how long does it take to encrypt and decrypt? Does this encryption scheme influence your real-time performance? The second one would be, does your encryption scheme also influence your control performance? Do you need to consider the trade-off between the system privacy as well as the control performance? Yes.
Yes, of course. At least for the second part, we always have to find balance between what is secure enough but isn't too tanky. I guess you can say it doesn't take too much to compute, because we are trying to implement it in real-life processes. For example, in this application, the whole evaluation of encrypted control law took 5 seconds, which was low enough for our application. But if you would want to provide, let's say, more secure or more complex setup, it would take, of course, longer. And what was the first question about encryption and decryption?
It's the real-time performance, maybe.
Oh, the performance of what?
Real-time performance.
Oh, real-time performance. Well, I'm not sure what exactly are you trying to ask there, but the longest part within this is the encoding in itself, because it contains the most complicated functions to do that. The encryption itself is then just polynomial multiplication that's usually done pretty quickly.
Yeah, okay. Thank you for your answers.
I think there was another, I hear it over there.
Hello. Again, thank you for your presentation. My question is very similar to the gentleman that just asked the question in terms of the theme of the study, which is cybersecurity focused. And you are using HTTP communication protocol. And I was also wondering, when you consider using HTTPS instead, which has a secure socket layer overhead.
Yeah,
And that's sort of what in my mind at least, the standard way of communicating online. But I know that it will add a real-time head and a secure handshake that will take up time, and that will also influence your control. So it'll be interesting to know and to test how big of an effect that overhead on your communication in your control loop will be.
Yeah, of course. We definitely plan on doing that. We just actually started to explore within this area, because so far, even like in general community, I haven't really even saw that many analysis for this, and I feel like this is vital part if you want to move to more real-life implementation. But of course, the HTTPS would be better option. We're just starting to explore and see like what takes the longest and how it affects the whole thing. But for the future, definitely.
Okay,
Yeah.
if
Thank
there
you.
are not any other questions, let's go to thanks again. And now we go to the next talk, that the name is Model Predictive Control for Tumor Growth, Detection and Desviation and Therapy Implication. Completely different topics. And the speaker is, your name?
Andrés Hernández Rivera.
Andrés. Okay, Andrés Rivera. Please go to the podium.
Hopefully it's okay. Hello everyone, my name is Andrés Hernández Rivera, and I'm here to present the work of our group. This is a joint project between the University of Seville and the University of Loyola Andalucía, both in the south of Spain. The outline of our presentation is as follows. I'll start with a brief introduction of what we're doing, then I'll describe the system at hand. We'll follow with the control model and optimization problem. Then we'll move on to the fault-tolerant approach that we've implemented, and we'll present some results and some final conclusions and final works. So, what are we doing? Here we are trying to improve the administration of chemotherapy, which, as unfortunately a lot of us might know, it is one of the main ways to treat and fight cancer. Cancer really is a family of illnesses that have common traits. Mainly, the main one is the presence of uncontrollably dividing cells that alter the normal functioning of tissues and organs that they are affecting. In this work, we've used a non-linear model that was implemented or was created by Chen in 2012 that considered different aspects relating to the treatment and the illness itself. The main ones are the pharmacokinetics of chemotherapy. Pharmacokinetics is just a realm of biomedicine, bioengineering, that studies and mathematically models the evolution and chemical transformations that a drug experiences in an organism. We also study in this model the tumoral growth and, most importantly, the treatment-induced immunotherapy, which is one of the main secondary effects, harmful secondary effects, that we're trying to limit. To control the treatment, we've implemented a linearized model predictive control, particularly a sequential quadratic programming, that calculates the drug, in this case of tamoxifen, which in humans is a very common chemotherapeutic agent used for the treatment of breast cancer. So we calculate the dose of that drug, and we administer it to the patient. In all of this work, the mathematical model and the patient is a common mouse, so they are not humans. Finally, we've also implemented a fault-tolerant approach to detect possible faults that might happen during the treatment. We implement some reconfiguration actions to try to limit the effects of the faults and try to prevent them from becoming a more serious issue. So, what is our system? As I mentioned before, this is a mathematical model of a tumor growth in a common mouse. So we will give the system the dose of tamoxifen, and it will go to the metabolization, also known as pharmacokinetics, of itself to reproduce those chemical transformation that it experiences. We also model the tumoral growth, as we mentioned before, and most importantly, the evolution of lymphocytes. Lymphocytes are one of the key type of cells of the immunological system of a patient, of a mammal, really, of all mammals. And we use them as markers to see how degraded or not the immunological system of the mouse, in this case, is. In terms of the control model, we linearize this very nonlinear model at each operating point. So we obtain matrices A, B, and C once a day, and then we use them to calculate the most appropriate dose of tamoxifen that we need to administer to the mouse. We do this process once a day because that's our sample rate, because we are implementing 1 year treatments for the mouses. So if we found that that sample rate is the most appropriate. In terms of the optimization problem, we have several objectives. The main one, as you might think, is to reduce the tumor volume as much as possible in the time we have for the treatment. We also seek to reduce the amount of drug that we are administering to the mouse. And finally, we are trying to degrade as minimum as possible the immunological system of the patient. In terms of the constraints, regarding the input variable, which is the dose of tamoxifen, we have a maximum amount, which is 800 micrograms per day. That is the maximum amount of tamoxifen that you can inject to a mouse. A larger dose than that might enter the realm of toxic doses, so that's something we want to avoid. In terms of the output constraints, I would remark the constraint F5B, That's the constraint relating to the lymphocyte. Thus, it is represented by a C because really we are trying to represent circulating lymphocytes. A common mouse, untreated, in a normal state, in a normal situation mouse, has around 10 million lymphocytes, around that quantity. So what we're trying to do here is we want to avoid that number from dropping to less than 40% of its regular value. So that's why we want to try to keep those lymphocytes above 4 million. In terms of the fault-tolerant approach, we've implemented a fault detection and isolation algorithm that uses parity equations and structural residuals. What we're doing here is that we are calculating the residuals for the different outputs, and then we've employed stochastic time-varying residual thresholds that we use to try to avoid the detection of false positives. With all of those, we are able to detect different faults, and particularly, we are able to detect the fault signatures for the different faults that we've described in this project. Each of the faults has one or a set of different reconfiguration actions that we implement to the system to try to mitigate or avoid more serious consequences of those faults. Here on the bottom of the slide, you might find a schematic of what we've implemented, where the SQP MPC calculates the dose and it is then administered to the patient. The outputs are measured and they are both logged back to the MPC and given to the fault tolerance strategy part of the algorithm that, if it detects the fault, will implement the different reconfiguration actions that we've defined to try to mitigate those harmful consequences. So, some of the faults we've gathered from literature are some of the most common faults that you might encounter during chemotherapeutic treatment. Particularly, F1 reflects an additional lymphocyte drop that is caused by viral infections, anemia, or the use of other drugs like opioids. This is important because since the chemotherapeutic treatment already debilitates the immunological system of the patient, we want to avoid that if an external caused drop of lymphocyte appears to worsen the state of the patient. This F1 has one reconfiguration action that is associated to it. So if regularly we had a maximum daily dose of 800 micrograms, we want to limit it to 100 micrograms per day. That way we leave the mouse, in this case, some wiggle room to try to recover a little bit, to try to get back to a more secure way to complete the treatment. The other fault that we've implemented is F2, where the patient, for whatever reason, we are not entering there, but like for whatever reason, stop receiving treatment administration. What happens here is that the patient misses some time of the treatment, so we want to catch up after it goes back to treatment to try to make up for that lost time that we had. In this case, the reconfiguration action associated with this fault consists of increasing the minimum tamoxifen dosage to 400 micrograms. Some other faults that we've implemented are the decrease in drug inhibition in the liver, the incorrect drug administration, or errors in dose calculations, for example. But we've limited this work into implemented those first two faults, F1 and F2. So regarding the results, as I mentioned before, we've done 1 year simulation of a treatment where we start with a mouse that has a 1,000 cubic millimeters tumor. We implement that tumor and its treatment, and we are checking the results of the system. As you might find, when F1, that if we remember is a sudden external drop of lymphocytes, happens, and it is remarked with a gray box. When it happens, the receivable detected, not only detected, but the algorithm kicks in the reconfiguration action that limits the administration of tamoxifen. You can see it, okay, perfect. In the upper part, in the upper graph, we've not implemented that reconfiguration action because we wanted you to see what happens if we let that fall happen without any action from outside. So, what happens here is that the tumor goes from the initial 1,000 cubic millimeters to 166 or 67, really, cubic millimeters. But the final number of lymphocytes is well below the 4 million constraint that we had. So the side effects in terms of the immunological system are too great for the mouse, and it could be a danger of common pathogens that are surrounding us every single day. If we implement the reconfiguration action, what happens is that the dosage of tamoxifen is limited well after the occurrence of the fault because we not only want to detect it, but like recovering from it, and we want the system to be in that recovering state until it is out of danger, per se. As you might think, and the results show, limiting the dose for a time will lead to a lesser decrease of the tumoral volume, and that's what happens. Instead of reducing the tumor from to 167 cubic millimeters, we reduce it to 250, around 250. That's we found acceptable to us because sometimes, especially with chemotherapeutic treatments, the treatment can become worse than the illness itself, and we want to limit those side effects because the lymphocyte count for that time that the fold is happening is too low, and it really poses a grave risk for the health of the mouse. In terms of the fold 2, we also see that the residuals, in this case residual 2, is able to detect the presence of this fold. And what happens when we do not implement the reconfiguration actions is that after the mouse goes back, well, in this case patient, goes back to treatment, for a couple of, well, 4 or 5 days, the MPC misses the chance to try to catch up on the treatment to try to reduce as much as possible the final volume of the tumor. As we see, the volume is 253 at the end of the year, and the lymphocyte in this case is not an issue. If we implement the reconfiguration action, we are able to get to around 25 cubic millimeters of extra tumor reduction that further increases the efficacy of the treatment by increasing, as we mentioned before, the minimum amount of dosage that the MPC has to administer. In terms of some conclusions that we found during this work, we found that the implementation and development of this type of algorithms serve as aid tools that might help oncologists, practitioners to develop more efficient and secure treatments that might increase the recovering chances of patients and their well-being during the treatment. Also, we've tried to ensure the improvement of oncological outcomes, showing the potential of this use in clinical practice. It is important for me to remark here that this is a first step in the development of all these tools, and the extension from mice to humans is a step in that travel, per se. And as all of the development of new biomedical bioengineering tools, we had to start with mouse then before we can move on to humans. Future work might seek to address unusual faults in cancer treatment, for example, some of the others that we left behind. We are also trying to implement new algorithms that try to guarantee that these strategies are effective, safe, and patient-centered. And with that, trying to improve as much as possible drug administration processes and in oncological therapies. So thank you very much for your attention.
Thank you very much for your talk. I open the discussion. There are some question, problem. Yeah, here one. Anyway. Please.
Thank you for a very nice presentation. My question is, have you considered analyzed the effect of model mismatch between the model you consider in, I guess, in MPC and the model for the mouse in the simulation?
Yes. In other work that we've implemented, not for this conference, but like for another work, we took into account a 1% mismatch between the mouse model and the patient in this case, and we implemented a stochastic MPC controller to try to account for that mismatch.
Perfect. Thank you.
Thank you.
Other comments or questions? If not the case, then we thanks again the authors, and we go to the last presentation before the lunchtime, and The title of the talk is Learning-Based Model Predictive Control with Uncertainty Estimation for Resilience, Microgrids, Energy Management. And the speaker, I think, is Victorio, yes?
Yeah.
Okay, you are the speaker.
Okay. Okay. So, hi everybody. I'm Vittorio Casagrande. Currently, I'm a postdoc researcher at University College London under the supervision of Francesca Bohem. And I'm going to present this work that is entitled Learning-Based MPC with Uncertainty Estimation for Resilient Microgrid Energy Management that we developed in collaboration with our collaborators, Martin Feriank and Miguel Rodriguez from UCL. So let me start giving an introduction on the topic of energy management for microgrids. So a microgrid for us is a cluster of loads, distributed generation units, and then storage systems that are operated in coordination to reliably supply electricity and connected to the power distribution grid. And an example is given here in the top right of the slide. We deal with the energy management controller, which is on the top level of control of the microgrid system. So here we have a schematic of typical way to deploy controllers for microgrid systems. So on the primary control, we have a function like frequency and voltage regulation, and at the top level, we find the energy management controller. And the main challenges that we deal with are dealing with the uncertainty in renewable power production, electricity price, and load demand. So basically, uncertainty affecting the microgrid system. And the second challenge is ensuring fault resilience. So we're basically asking what happens if a fault, like a blackout, happens, and then we have to switch the operation of the microgrid from a grid-connected mode to a high-landed mode. Our goal, in general terms, is to design an online learning and based MPC algorithm to schedule the microgrid operation, and that is able to adapt to possible changes in the environment. So before going into the details of the method, let me say something more about the challenges that we are dealing with. So in this slide, I'm listing the two challenges we are mainly dealing with in this work that are uncertainty and ensuring fault resilience. So by uncertainty, using a control system terminology, we can divide uncertainty into model uncertainty and external disturbances. By model uncertainty, we mean, for example, the energy conversion losses of the battery, so uncertainty in the model of the system. And by external disturbances, instead, we mean other kind of disturbances like the load demand or the renewable power generation that are uncertain and are affecting the microgrid operation. So here I'm giving an example of two different types of load demand. So we can see from this one, the top one, that there is it has a periodic behavior, and it's typically the load is turned on for 5 days a week, and then it's turned off during the weekends. Instead, the second one, this one, is a bit different because it is on every day, but there is a sudden change in the average value of the demand on this day. And this can be due, for example, to an installation of a new equipment or new machinery. And what we deal with is, what we want to do is design an algorithm that is able to adapt online to these kind of changes. And then we want to ensure fault resilience. And this is typically done in the literature by implementing two different strategies. One is called proactive scheduling, and the other one is called outage management. And by proactive scheduling, we mean that we want to ensure to be ready for the fault once it occurs. Instead, by outage management, we mean that we want to deal with the fault in an optimal way. And in particular, in this work, we deal with external disturbances and ensuring proactive scheduling. So our goal is to design a resilient proactive scheduling strategy, explicitly considering the uncertainty in the predicted variables and the probability of fault occurrence. So a bit of listing, I'm going to list here the contributions and what are the main difference with respect to works in the literature. So typically in works in literature that deal with resilient strategies for microgrid systems, a fixed amount of energy is devoted for fault resilience. And it does not change, it is not adapted, it may not be adapted to the future load demand. So this means that less storage capacity is available for the other EMS goals. And this, at the very end, turns out as a financial loss. Second thing typically work that deal with resilient energy management, either they assume to know the future uncertain profiles, and they do not adapt to this uncertainty. So they assume basically to know what are the future value of the profiles. And finally, the probability of fault occurrence is an information that we can use in the design of the energy management system. And basically this means that if the probability of a fault occurrence is very low, then we don't want to store a huge amount of energy. The main contributions of our work are listed here, and this is an online estimation algorithm for the future profiles as well as their uncertainty. And the second one is a proactive scheduling strategy based on stochastic MPC. So here I've written the typical way to enforce a proactive scheduling constraint. So we want the stored energy to be greater than the load energy requirement for the next, for example, 3 hours. Instead, what we propose is to reformulate this in this way. So we want the probability of this constraint to be enforced to be greater than the probability of fault occurrence. This because if the probability of the fault is very low, we don't really care about enforcing this constraint. Instead, if the probability is high, then we want to be sure to enforce this constraint. And we want to take into account the uncertainty in, for example, the prediction of the load requirement. So very quickly, this is the model of the microgrid we use. So we have a microgrid, for example, the one in the slide here. And this is composed of renewable generators and loads, which basically for our goals, the only thing they do is injecting and drawing power from the grid. Then we have a power balance constraint that is interconnecting all the different agents. Here in particular, we have grid connection, storage system, S, and R and L stands for loads and renewable generators. And then we have a dynamic model for the storage system, this one, subject to constraints or in input state. And finally, the goal we consider for the energy management system is the minimization of the total energy cost. So we want P is the price of electricity, and PG is the power that we exchange with the grid. And we want to minimize this over the whole operation of the microgrid. The architecture that we use is the standard architecture that we show here in the slide. We have a predictor that in our case in particular is a neural network predictor that takes some feature as input and outputs the prediction of the uncertainty. So for example, the future load demand over the next day, hours, or whatever. This is then used by the optimizer here for the scheduling purpose of the AMS. Basically computing how much power, how much energy we are storing at each time step. And this signal is then sent to the microgrid system that gives back the state. And we implement this in the MPC framework, so this is why we have this feedback loop. I will not go very much into the details of the online learning algorithm since we proposed it in another paper that is reported here, but very briefly, at each time step, we adapt the weight of the neural network in order to take into account the most recent information we have. So for example, to be able to adapt to the change in the load demand that I showed, for example, in the previous slide. And we do this by minimizing, at each time step, an MSC loss. So we penalize the difference between the prediction and the real value of the uncertain variable. And again, this is done online. Second thing, we have the optimizer, so that minimizes with respect to the power input and output to the storage system. This is the financial cost that I said before. Model of the microgrid, limits on states and inputs, power balance constraint. This is the initial state, so this feedback. And finally, the proactive scheduling constraint. This is like the standard way to implement this. So we want the state of the system to be greater than a certain value at each time step. And this value is calculated as the future load demand. And note that the future load demand is the predicted value. It's not, we don't know what the actual value is. So there are two main drawbacks of this method of enforcing the proactive scheduling. The first one is that we assume that a fault can happen at each time step. So even if the fault probability is very low, then we are still storing an additional amount of energy, and we don't want this. And the second thing is we do not consider the prediction uncertainty. So for example, a renewable generator, a power photovoltaic generator is not producing energy at all during night. Instead, it is producing a variable amount of energy during the day, and we need to take this into account. So what we propose is this resilient stochastic energy management. So first thing, we extend the online learning algorithm in order to estimate not only the expected value, but also the variance of the prediction. So by basically what we do, we model the certain variables, so the load demand, the renewable generation, and so on, as Gaussian variables, and we minimize this negative log likelihood loss. Basically, so the neural network is outputting, instead of outputting only the expected value, the mean value is outputting the mean and the variance of each, for example, of the load demand. And then we reformulated first we formalized the chance constraint, and then we reformulate it in a deterministic way in order to be solvable online. So this is our constraint. We want the probability of the state of charge to be greater than a certain value, that is the future load demand, greater than a probability P, that is the probability of fault occurrence. This can be rewritten in this way. So where this delta is a sort of safety band. Then we use Cantelli's inequality to rewrite this. So I will go fast into this. You can find more details in the paper. We compute the variance of the state of charge of the battery, and then we can reformulate this in this way. So we want S hat, the expected value of the storage, to be greater than what the future load demand, the future energy demand for the next steps, plus a term that takes into account the probability of fault occurrence and basically the uncertainty in the prediction. So I will go now to the experimental results. And first I'm presenting the results related to the uncertainty estimation, and then the result related to the resilient energy management. So we can see here in blue, we plot the ground truth, so the actual profile of the load demand, the renewable generation, and price. In orange, we plot our prediction. And this pink-orange band represents the one standard deviation. And so we can see that we can typically predict quite well the renewable generation, especially. Then we have, for example, a peak here in the load demand that we cannot predict, and we don't predict very well. And we validated this using this 68, 95, 99 rule. Basically, we want a certain number of samples, percentage of samples, to be within the uncertainty band if we consider the 1, 2, or 3 standard deviations. And we have 69 here, 93 here, and 98 here, so the prediction works quite well. Then we go to the resilient energy management. So again, we enforce this constraint. We want the probability of the stored energy to be greater than the load requirement. And we want this to be greater than the probability of the fault occurrence. And we have rewritten this in this way, where, again, delta takes into account the probability of fault occurrence and the uncertainty in the estimation. So there are 3 facts that I want to show. The first one is that more energy is stored in the moments of higher uncertainty. And we see it from here. So this delta, this safety band, changes for different values of P, of probability of fault occurrence. If the probability is higher, probability of fault occurrence is higher, then we store more energy. And also we can see this periodic behavior that is due to the renewable generation. We know almost for sure that the renewable generation is going to be at 0 during night. Instead, it is very variable during the day. Then we see that more energy is stored when the fault probability is higher. So in this case, we simulated a change in probability of fault occurrence in this way. So the probability changes from 0 to 0.5. And we see that we are storing an increasing amount of energy here and here. And finally, say the bad thing about this is that there is a trade-off between resilience and economic performance. So as we increase the probability of fault occurrence, or as the probability of fault occurrence increases, we have a we have to sustain an additional cost. So this is basically the drawback of implementing a fault resilience strategy. But let me highlight that the probability of fault occurrence can be adapted over time. So most of the times it's going to be 0. Then when, for example, a weather event happens, then this increases. So in conclusion, we proposed a novel proactive scheduling strategy for resilient microgrid energy management. We basically did two things. We extended our online learning algorithm to estimate the uncertain profile, both mean and variance. A second thing, we designed the stochastic MPC algorithm to enforce the proactive scheduling as a chance constraint, considering the prediction uncertainty and the probability of fault occurrence. And as a result, we have a reliable estimation of the prediction uncertainty and an enhanced resilience of the system. And let me highlight that this method has been tested for the microgrid energy management case, but it's actually applicable to any MPC algorithm. You can find our code here on GitHub, so feel free to fork and start the repository if you like it, and adapt it to your algorithms if you want. As for future work, we want to extend this chance constraint to all system constraints and the online estimation, and we would like to online estimate the probability of fault occurrence. Okay, so I think I am in time. So thank you very much for your attention, and I'm open to some questions.
Thank you very much, Victor, for the presentation, and I open the discussion if there are some comments. Okay, here you have one, two. Go over here.
Thank you for this inspiring presentation. I have one question regarding the uncertainty estimation. From my understanding, you have used the maximum likelihood ratio method to estimate the uncertainty. My question would be, how can you integrate this uncertainty estimation in this MPC problem formulation? Do you also consider this estimation covariance matrix in this optimization problem? Yes.
So, short answer is no, meaning that we had to make some assumptions. This is like the first time we introduced this algorithm, so there is like room for improvement in here. And as I said before, we can extend this to a general control framework where we estimate the covariance matrix, and we need to adapt the MPC problem as a consequence. So the answer is no, it's not implemented yet, but it's something we can do.
Okay, yeah, thank you for your answers.
There are another question, I think, over there. Yeah, you.
Thank you for your very interesting presentation. And I was wondering about the computational aspects of your approach. We did something a bit similar with load scheduling in a similar scenario. And it was a mixed integer problem, so quite complex to be solved. And we noticed that it was quite a challenge to solve it, okay, in a reasonable time, okay? And you use a stochastic approach, so I think it should be quite slow, but you have plenty of time to calculate it. Could you please discuss how long is your prediction horizon, how many inputs you have, just to understand how heavy from a computational point of view is your approach? Thank you.
Yeah, so there's a simple answer to this, which is sampling times of this application are typically quite large. So this is not typically a problem. And even if you work with a sampling time of 15 minutes, you get plenty of time to do this, because this is typically convex optimization. This is not mixed integer. And so for this specific application, this is not a problem. And we tested the computational time of the algorithm. It runs on my like normal, say, laptop in like 1 second or something like that. And this is non-optimized Python code that is basically the one you can find here. And I'm very confident that by writing like a proper implementation or proper hardware, you can speed up this very much. But yeah, so for this specific application, I don't see an issue. And we are actually thinking right now as methods to basically simplify the mixed integer, if we want to deal with mixed integer problem, reformulate the mixed integer problem as a non-mixed integer problem. So we don't want to use integer variables. We are thinking about this, but it's an open problem, so wait, stay tuned and there may be some results.
Some other question, other comment? I have one comment related with if there are multiple faults in the case, how it changed this if really there are two events simultaneously or there are so uncertainties in the system. If you can't...
you're talking about faults?
Fault, yeah.
Okay, so in this case we considered only a fault, a blackout fault here. And
but even there could be a lot of things there.
Yes, so on the energy management aspect, the point is each element of the microgrid is basically a power source or a power sink, okay? Can exchange, so this is the aspect we are interested with. Then, yeah, I agree that different elements respond in a different way, so I think it's quite easy to, let's say, introduce more domain knowledge in this and modify this problem. We have the requirement that the problem has to be convex, but there are convexification methods. So yeah, again, it's something that can be done for a specific problem.
Okay, thank you very much. If there are not any questions, we thank all the speakers and the audience, and let's take your lunch.
Thank you.
keynote speech. So I'm very happy to introduce the last keynote speaker. She's Professor Ping Zhang. She's a professor and holds a chair for automatic control at the University of Kaiserslautern, Landau in Germany. She received the Bachelor Engineering degree in Automation Control for Hangzhou University of Science and Technology in Wuhan, China in 1997. And the Master's Engineering and both also the PhD degrees in Control Theory and Control Engineering for Tsinghua University, Beijing, China in 2002. From 1999 to 2001, she was with the University of Applied Science, Leipzig, Safeprocess, Germany, in the framework of the AAD sandwich program. From 2002 to 2007, she worked with the Institute for Automatic Control and Complex Systems at the University of Duisburg-Essen in Germany. She collected industrial experience as the BASF Sweden in SE in Ludwigshafen of Germany, the world's largest chemical producer by revenue, and actively contributed to plan asset management, which combines fault diagnosis and predictive maintenance, and embeds them in industrial plant organization activities. Before joining the University of Kaiserslautern Landau, she had been a professor of automatic engineering at the Rhine-Waal University of Applied Science, Kleve, Germany, from 2012 to 2013. Her research interests include model and database fault diagnosis, fault-tolerant control, cybersecurity of control systems, data-driven control design, discrete event systems, Boolean control networks, building energy efficiency, and various industrial applications. She is co-author of 49 journal papers, 122 conference papers, and 2 United States European patents. She led the NAMUR, User Association of Automation Technology in Process Industries, Working Group 413, Asset Management, from 1211 to 1213. She is a member of the IFAC Technical Committee, of course, the SAFEPROCESS, and has started the working group Industrial Application of Advanced FDI FTT Technology of the IFAC Technical Committee 6.4. She serves on the industrial boards of several international journals, including Control Engineering Practice. Please, Professor Zhang, the stage is yours.
Yeah, thank you very much for the introduction. So it's my great pleasure here to give the talk on detection and avoidance of cyber attacks on industrial control systems. So we know that nowadays in the production plants, between the different system components like sensors, actuators, and controllers, there are more and more networking. And all the plant owners and automation suppliers are preparing for the solution of cloud-based control, cloud-based remote monitoring, which use the network as a central communication channel. So on the one side, so it makes, the network makes the plant to be more flexible and reconfigurable. On the other side, we know that through the network, so maybe the cyber attacks can happen. So attackers may get into the system. So here from our control viewpoint, we can always abstract the system as we have the plant to be controlled, and we have the sensors to connect the information. We have also the actuators to influence the plant behavior, and our controllers now receive the information from the sensors through the network, and also the controllers calculate the control inputs and send this information over the network to the actuators. So now, if the attacker gets into the network, they may, if stop the signals transmitted over the network. So the control inputs and the sensor outputs, and they may even manipulate the signal values. They may change the values of the signals transmitted over the network. So that means for us, it is a practical situation that the risk of cyber attacks has increased significantly during the last years. And here are several examples of cyber attacks. Most famous one, 2010. So there was Stuxnet targeting at DCS from a very well-known provider. And in the year 2014, there was an attack on a steel plant, which has caused explosion. 2015 attack on an electricity grid, which led to the interruption of the electricity supply. In the year 2017, so very famous attack, the called Triton attack has happened in a petrochemical plant. It has shocked the industry a little bit because they have targeted on the safety systems. So before that time point, people have always thought that the safety systems are very well protected. So very little people have access to that system. But Triton has happened at the end of 2017. And also in the year 2021, there was an attack in the USA on gas line pipelines, which led to the interruption of gas line supply. So here are some practical examples, and indeed there are much more reported in the press in the last years. So currently what happens in the industry is that, so the big enterprises, they are building up cybersecurity task force teams to handle this problem, to protect their production plants. And what have been usually taken as measures in the industrial system, or for instance, installation of firewalls, to have some access control, to let people only access the information that they absolutely need. And from the communication side, there are also some network intrusion detection systems. So most of them, the basic idea is namely to analyze the network communication pattern. So namely, so which node sent how often, which information to which other nodes. And if there's some abnormalities, then some alarm will be triggered. But these measures are not enough for the protection of our industrial plants. So we will show it a little bit later. So there are several types of attacks which cannot be detected by such intrusion detection system and also by the standard diagnosis technique. So now the question is, there's a big need for new methods to improve the cybersecurity of our industrial systems. And what we're going to do here is namely to develop some measures which are complementary to the communication and computer science. So surely we will still have the measures and we need them from the communication and computer science, but we need also more measures which takes into account that in industrial control system we have some physical plants. So the signals, they cannot change arbitrarily. So there's some internal relationship so between the control inputs and and the sensor output. So we can make use of that connection to help us to improve the cybersecurity. So if we look at the cybersecurity problem, so we may classify the problem into several different types. So at first, so how to describe the cyber attacks? So those attacks that get into the system through the communication network. Second thing is that, so how big is the risk? So how to do the cyber risk analysis? How realistic are the risks? And if an attack has happened, so in the control system, so how to detect those attacks as quickly and reliably as possible. So that is our typical attack detection problem. And also, you know that to detect after something has happened, it is an reactive measure. So could we do something more? Could we try to reduce the risk of cyber attacks, try to avoid it? That is a big topic. And so what we hope is that we can achieve some kind of resilience, to have some defense in depth to protect our control systems against cyber attacks. So now, at first, if we look at the modeling of the cyber attacks, so indeed, there are many different kinds of attacks. They are different in several aspects. So the first thing is which access, which writing and reading access do the attacker have to the communication channels? So which channels could they read, or could they both read and write? And the second thing is how much pre-knowledge does the attacker have regarding the plant model. So how much they know about the plant. The third thing is that how much the attacker knows about the control theory. So do they have some background in the control, they know some control approaches or not. And based on these different aspects, so we can classify the typical cyber attacks into several classes. So the most famous cyber attacks is the denial of service, the DOS attack. So that means the network cannot carry out the function. So it can be achieved through network jamming. So the attacker may send many messages and to block the network from providing the service. On the other side, so denial of service is indeed quite easy to detect. So if the controller cannot get the sensor information, surely we know that an attack has happened. And second type is the bias injection attack. So here, the attacker tries to change the value of the signals transmitted over the network. And if they just change the values without much correlation between different channels, so they are the bias injection attack. And this kind of attack can indeed be detected with the well-established fault diagnosis approach. So with the standard approaches that have been developed in our community to detect it. So it is also not a problem indeed to detect. But there are also some more challenging attacks which are marked here with the blue color. So the so-called replay attacks, covert attacks, zero dynamics attacks, and mirror attacks, which was shown recently. So now let's have a brief look at what it means. So at first, the replay attack. It is indeed a quite easy attack. The attacker doesn't need much pre-knowledge about the plant. So the attack is carried out in two steps. So in the first step, the attacker indeed doesn't do much. They just eavesdrops the signals to collect the information that are transmitted over the network to connect the control input signals and the sensor output signals. And they just save the signals. So now in the second stage, what the attacker do is, namely, they will wait for a suitable time point, and then they will cut off the connection between the process and the controller here. So you see that, so the connection is indeed totally broken here. And what the attacker does is that they will replace the true control input signal from the controller, that is a U star here, by his attack signal UA. And on the sensor output channels, the attacker will replace the true sensor output signals by here the connected signals. So they will replay then the recorded output signals. And our monitoring system is sitting on the other side of the network, so namely on the side of the controller. We'll get only the information of U star and Y star. So here, indeed, the standard monitoring system cannot see much of the attack. So that is the replay attack. And now come to the covert attack. So covert attack is much different than the replay attack. So here, the attacker has the information of the plant model. So what the attacker does is, namely, on the one side, so he will here manipulate the signals transmitted in the control input channels. So namely, the UA here is the input attack. And you know that if we have a linear linear time invariant system, then there's this very famous superposition principle. So that means it is no problem at all if the attacker has the process model. They can exactly calculate what is the influence of the input attack UA on the sensor output Y. And then he will subtract this calculated value from the true sensor output value. Now our monitoring system will get the information between the U star and Y star. So in the Y star, there's no information about the attack at all. So it is not possible for the standard monitoring systems to detect the presence of UA and YA. So you see that here the attacker coordinates his attacks in the control input channel and in the sensor output channel. So UA input attack is used to influence the planned states, to do something that the attacker desires. And the YA in the output channel, the output attack, that will compensate the influence of the input attack and to make the attack stealthy. So that is the covered attack that makes use of the superposition principle. And in the other type of attack, so zero dynamics attack, so here it makes use of another property. So we know that if the system have some zeros, then the system zeros have the so-called blocking property. So that means some specific type of control inputs are not visible in the output. So namely, if the control input, if the input signal, so this input attack is constructed in this way. So here this term related to the position of the zeros. And now if the zero of the system is on the right half complex plane, so in that case, we have that this exponential term may get increased very rapidly. So that means now the input attack, UA, will influence the planned states, but his influence is not visible in the sensor output Y at all because of the zeros. And so in this way, for our monitoring system, it's also not possible with a standard monitoring system to find out the presence of this input attack UA based on the U star and Y star here. So the last kind of attack we want to have a brief look is namely the so-called mirror attack that have been revealed recently. So this mirror attack is indeed a combination of the replay attacks and the covered attacks. Similar as in the replay attack, so the mirror attack will cut off the connections between the controller and so the controller here and the plant. So a cutoff here in the input channels and output channels. But now, instead of trying to compensate the influence of the input attack on the sensor output attack, so in the mirror attack, they do it differently. So they use also the plant model and to calculate the output, simulate the plant behavior and calculate what the plant output should be if the control input is the true one U star. And then he replaces the true sensor output from the plant by the simulated output. So if his model is good, then he can calculate this behavior very well. And again, it is a challenge for our monitoring system to detect the presence of this UA and YA here. So now, if we briefly summarize the several types of attacks we have seen just now, we see that, okay, so the replay attack, covered attack, and also the mirror attack, they need access to all the control input channels or the sensor output channels. So the covered attack, mirror attack, and the zero dynamics attack, they need, all of them need the process models. So the people from the industry may ask, if the attacker can only have access to a part of the sensor signals or control input signal. They don't have access to all the signals, partial access they have. Is there still a big risk? And second question is that, in the industry, it's indeed not so easy to get an accurate model. So if the plant model that is available, so maybe inaccurate, so maybe I'm secure, so maybe the attacker cannot do much. So we have investigated so this problem as well. And the conclusion is that, well, even if the attacker has only partial access or has some inaccurate plant model, so the risk is still there. Let's look at two examples. So in the first example, so namely in the covered attack framework, assume that the attacker now has access to all the control input channels, but he has only access to a part of the sensor signals. So namely, the Y1 here, it cannot be manipulated. It is well protected by the plant. And the Y2 here is unfortunately not protected. That means here the attacker has only partial access to the Y2, can manipulate Y2, but can do nothing to manipulate Y1 here. So now, what the attacker indeed may do is that if he has the control background, he may think about, okay, so in the control input channels, he can impose some control input attack, the UA here, and he can compensate the influence of the input attack UA on the Y2 because he can manipulate Y2. So he imposes YA2, the output channel, the output attack in this channel. But because the attacker cannot manipulate Y1, then he just tries to decouple the influence of UA on Y1. That means the UA will be designed on the one side to satisfy his attack goal. On the other side, the UA will not influence Y1 here. It's indeed not a difficult problem. And in this example here, so if we design, introduce this decoupling block and make the product of the transfer function from the control input U to the Y1 multiply with the decoupling block PS to be 0, and in that case, we can already achieve this decoupling. So in that case, that means even if the attacker has only partial access to the sensor output channels, but they can still keep their attack to be stealthy. So that's the answer to the first question. And look at the second aspect. So if the attacker has only an inaccurate plant model, they can still make the attack invisible. And if we take the covered attack as one example, you know that the attacker has an incorrect model, but he has also some real-time information. So he can read the control input signals and the sensor output signals in real time. He may use of this online information to adjust the UA in the input channels so that the influence, even if there is model uncertainty, the influence of the control inputs UA on the sensor output Y is very deterministic. So in that way, he can still compensate the influence of input attack on the sensor outputs. So that's a so-called robust covered attack. And we have also found out recently that so if the attacker imposes the mirror attack, it's even simpler for him to make his attack stealthy, even if he doesn't have a good model of the plant. So namely, he can use the extended Kalman filter to do that. And we know that extended Kalman filter is included in, if not in master, but in the master courses. So it is so very, very well known. That means it's indeed not difficult for the attacker to realize a stealthy covered attack or mirror attack, so in the real systems. So now the question is, so how to cope with such big risks and how to detect the attack. So we want that if an attack happens, so it can be detected early and reliably, so that so people can take some countermeasures. So here for the attack detection, we have developed several approaches in the recent years, and the modulation matrix approach can be used to detect the covered attacks and zero dynamics attacks. And if we use the so-called nonlinearity approach, so we can detect the replay attacks, inspired by the idea of a honeypot in the communication technique. We have developed one approach to use some auxiliary system to make the covered attack to be better visible. So if the people doesn't want to change the control input channels, and also inspired by the communication technique, we have used the so-called frequency hopping approach to detect the covered attacks. So now I would like to take just two of them as one example. So at first, we look at the modulation matrix approach, a very simple approach. So here we investigated in the framework of a covered attack. So as mentioned, in the covered attack, the attacker will impose the UA in the input channels and simultaneously compensate the influence of UA on Y by imposing the YA here. And the idea of the modulation matrix approach is just to introduce, so we see that in the control input channels, there is the SK, so the S modulation matrix is introduced. So it can be a very simple, so it is a constant matrix, or later we make it also to be time varying. And after that, so everything is standard, so we can use the observer-based approaches that is very well studied in our community to design here observer-based monitoring systems. So let's check what happens now if we introduce the modulation matrix. So because of the modulation matrix S here, so now in our plant, in the control input channels, so we have, instead of B, so here we have B multiplied with the modulation matrix S. And because of if the attack, so we have the real control input is namely the control input calculated by the controller U star plus the input attack UA here. So that's a change in the state equation and in the output equation. And now, on the other side, so when we build up our observer-based monitoring systems, so the plant owners know the existence of the modulation matrix, so that he can build up his observer. So in this way, so here we have also the BST here. And now, if we look at the dynamics of the residual signal, surely we need to keep the information about the modulation matrix S to be secret. So it must be kept secret. So the attacker doesn't know the existence and the value of the S here. So now if we look at the dynamics of our residual signal, so we see that, so that is our residual dynamics, so the state equation and our residual is the R here. And what we can read out, so from the equations, is namely the residual signal R will be influenced not only by the disturbances, unknown disturbances, they will also be influenced by the input attack UA here. And you see that, so if there's no modulation matrix, that means the modulation matrix S here, it is just an identity matrix, so we do nothing. And in that case, you see that, so this term will be 0. So that means, no, we cannot see the influence of UA, but we have introduced the modulation matrix, and each is not an identity matrix. So we can see now the influence of the input attack UA on the residual. So with this residual signal, we can detect the presence of the input attack UA. And surely we need to take care when we design the modulation matrix S, we want it on the one side to show the presence of the attack UA. On the other side, we want to reduce the influence of the UA on the system states. So there is an approach how to select the modulation matrix. So the advantage of this approach is that here the design of the modulation matrix and also especially the implementation of the modulation matrix is indeed quite simple. And this approach is also available to zero dynamics attacks or the mirror attacks here. And in order to make it difficult for the attacker to find out the modulation matrix, we can use time-varying modulation matrix for this purpose here. So that is the first approach about the modulation matrix. And the second approach I want to show here is namely to detect the replay attacks. And in that case, so we know that in the replay attack, the attacker will break down the communication between the plant and the controller. So you see that the communication channel is broken up. And he imposes UA and he replaces the YA here. If the attacker waits for a suitable time instant to start with the replay, then it's very difficult to detect his stealthy attack. And so the basic idea now is that, so we must do something that the attacker doesn't know. And if the attacker doesn't know that, so he cannot react to the changes in the plant. And then if he gets access, manipulate the signals, we will notice that. And to do that, so we have worked out a rather simple approach. Namely, we will insert a small nonlinearity unit in the feedback loop. So you see that, so that is a standard controller. And here the psi is some small nonlinearity. Could look very simple, like this two-point controller with hysteresis, has only two parameters. Then you see here we have a switch. So that means, so in most of the times, the switch is just closed, is just opened. It will not disturb much of the normal operation of the plant. And from time to time, so at irregular time instants, we will then close this switch. We will insert this nonlinearity loop. And we know that, so if the plant has no path behavior, then we can adjust the parameters of this nonlinearity here and to generate some oscillations, small oscillations, so very, very small oscillations in the system. And what's more convenient is that, so if we adjust, so this parameter C and the D here, in this nonlinearity, we can change very easily, so the frequency and also the amplitude of the oscillation here in the plant. So that means, so later with some standard signal processing technique, we can detect the presence of the oscillation and we can find out the attack. So that is the basic idea of the nonlinearity. So in general, in our control field, so usually we don't like nonlinearity, but here make use of small nonlinearity, and indeed we can improve the security of our plant. So now we have worked out some approaches for the attack detection. So the question is, so how about the real systems? And will they work so in the real plants? That's why we have carried out some benchmark study to check so how easy or how difficult it is to detect the cyber attacks. And for this purpose, we have seen that in the Singapore at the University of Technology and Design, so they have built up some iTrust Center, so that is the research center for cybersecurity. And this iTrust Center has launched so several benchmarks, and they provide some real data connected from the benchmark plants to worldwide to the researchers. And we have at first looked at the so-called water treatment plant, because we know that in the critical infrastructure, for instance, in the water, in the electricity, so they are the things that we need need in the everyday life. So without water or good quality from water, so there will be some problem in our society. And so we have looked at first the water treatment plant, and after that we have looked at the water distribution plant that is also provided by the iTrust. And here's a picture of the water treatment plant. So it is a scaled down real industrial water treatment plant. We have also talked with one of the biggest water treatment plant in Europe, and in their opinion, so this benchmark is confirmed that it is a rather good benchmark, shows the essentials of the industrial plants. And so this water treatment plant includes 26 actuators and 25 sensors, and the iTrust people have implemented 36 attacks. So there are also some single attacks, there are also some multiple attacks. That means multiple signals were manipulated simultaneously. And so indeed, so 31 of the attacks have been successfully carried out by the iTrust. The other one were documented, but it is not, indeed not successful. And so when we started with this benchmark study, we have thought at first, so we just use the standard for diagnosis and check how far we can go with our available approaches. And because it is industry near system, so you know that in the industry, the factories usually have some limit value checks, have some safety rules that must be obeyed, so why not use them? So surely, so at first we, by looking at the mechanism of the system, we have built up some very simple limit values and safety rules. And so we have tried to do it as the procedure in the industry. And after that, we have seen that in the water treatment plant, so we have here 3 tanks. So these 3 tanks looks quite like, so I think in many laboratories we have the 2-tank system, 4-tank system, 3-tank system, looks quite like that. So the idea here is that why not build a model? So the tank system is indeed not difficult. And then we have identified a model for these 3 tanks, and the model works quite well. And because we have the model, then we build up a model-based monitoring system for this part. So that is the gray part that you see in the figure. And in this benchmark process, there are still a large number of other signals which we don't know the mechanism, and we have only the data. So for that part, we have used the data-driven approaches. And when we designed the system, so we kept in mind that in the industry, so usually you don't have much attacked data. You have usually attack-free data. So we have used for the design of the monitoring system only the attack-free data. And so this result was presented in the last SAFEPROCESS in Cyprus, and we can detect all the 31 successfully launched attacks, and by the combination of these workflows, of these procedures. So what we see from this example is that, so at first, the standard fault diagnosis technique can contribute a lot to improve the cybersecurity of industrial plants. The second thing that we see is that, so the iTrust Center, it seems that they don't have much control background, so they didn't really implemented the sophisticated cyber attacks. So there's no replay attack, cover attack, and so on. So that's why it works already very well with standard fault diagnosis technique. And in the last year, so we have handled with the problem. So you know that if you have a big plant, if you know that something is wrong, an attacker had get invaded in that, so you want to know which part of the plant, not to reduce the time for the troubleshooting. So one of our PhD students has looked at the attack isolation problem. And we have found out that indeed we can isolate most of the attacks. There are several attacks which are denoted by the circles here. So we cannot tell exactly which attack it is, but we can reduce it to a much smaller group. So we can reduce the range of the troubleshooting. So here we are going to do some work after that, and to think about what we can do. So not only from the isolation approach side, but also from which information we need in it. So after that, so for us, it's the question, so how good is the method we have used? So this combination of the safety rules, limit value with model and data-driven approach to other processes. So we have used exactly the same approach and consider the second benchmark from the iTrust Center. So that is the water distribution testbed, and it works quite well for the attack isolation. For the attack detection, so the master student at that time has just spent about 2 months and have got a very satisfactory detection system. And what is interesting, so in this water distribution plant, is because at first it has much more signals than the water treatment plant. It has more than 100 sensor and actuator signals. And the second thing is that there are also many binary signals inside, not only continuous valued signals, but a large percent of signals are binary. So how to cope with that? Because it's an industrial practice. And here they have implemented 15 attacks, and we have got a satisfactory result. And currently we are looking at an electricity grid provided by the iTrust, but we have found out they have provided this time for this benchmark mainly the attack-free data. So the attacked data is not provided in a format that normally person can interpret, can read out by the program. And so if anybody in the society have some electricity grid with the possibility to implement cyber attacks, it would be our great pleasure to do some cooperation and to look at that. Okay, so now we have looked at, so if an attack has happened, so how to detect it. On the other side, you know that if you detect something, that means, so this is something that you don't want has indeed already happened. So it's reactive. No? So something has already happened and we try to react to that. The question is, could we do it better? Could we try to avoid it? Could we reduce the risks that the attacker impose an attack at all? So that is the question we want to handle, and the key here, to put it in simple words, is indeed idea is simple. So we want to protect the signal access, signal information, and also the plant model knowledge. And here we have again different possibilities in it. So one possibility is that we do some encryption. You know that in our emails, so it's, and also in our data storage in the cloud, so we can do the encryption indeed quite well. Why not use it for the industrial applications? And in the computer science, it provides also some other techniques, for instance, the so-called secret sharing. So namely, if you want to transmit the signals over the network, so you can transmit it, you can divide it, split it into several shares, and only the person, the recipient with enough percent of shares can reconstruct the original data. So have we investigated how to do that for our control systems. And here I just want to show what we have done in the encrypted control, because it has given us at the end some very surprising result, because indeed we can, you know that usually encryption only ensures the confidentiality of the data, so that the attacker cannot read out the information in the data. But indeed, if we do something more, we can also achieve the resilience. That means if the data is manipulated, we can indeed cancel out that influence. So now come to the encrypted control. So how we did it step by step. The basic motivation is namely, so we want to protect the confidentiality of the process data transmitted over the network. Also, so if we put, for instance, our data in the cloud, and here we put, if we put our controllers in the cloud, in cloud applications, we want also to protect our controller information, because we know that controller is indeed the heart, one of the most important components in an industrial plant. We want to protect that information from the cloud providers to avoid that the honest but curious cloud providers get information about the controller that has been put on their platforms. And by protecting the confidentiality of the data, we can avoid that the attacker read out the two input signals and also the sender output signals, so we can reduce the risk. We cannot avoid, but we can reduce the risk that they get a good process model. That means we can use encryption technique also to help us to avoid, to reduce the challenging attacks like covered attacks, zero dynamics attacks that need the plant model. So here, for that purpose, we have started with the classical approach to get to know how the encryption indeed works. So here, our sensors has measured some physical variables and get the information, and then we encrypt the sensor signals and send it across the network, and then we will decrypt the ciphertext and get it again in plain text. And the controller will calculate the control inputs based on the plain text of the sensor signals, calculate control input signals, and then get it encrypted again, because he wants to send the information through the network. And then the ciphertext is sent through the network to the actuators. So if we do the encryption in this way, what we protect, or namely, so here's the red part, so that all the sensor signals transmitted over the network, and the control input signals transmitted over the network. But we cannot protect indeed the cloud providers, the third-party platform providers to get information about the controller, because the controller parameters are still in the plain text form. So to go one step more, we can think about, could we achieve some end-to-end encryption? So that means as soon as the signals from the plant leave the plant, they will only exist in the form of ciphertexts. No? And so that people cannot read. And only when the signals come back to the actuators located near the plants, it will exist again in the plain text. That means we want to protect the whole channel, so the red channel here, also the controller parameter. So you know that, so what the controller indeed did? So if we have a state feedback controller or observer-based controller, so the controller indeed does some calculation, has some multiplications, additions, do some calculations. So we will carry out the calculations inside the controller, also based on the ciphertext. We don't want at any time have the plain text here. So this is indeed possible because in the communication technique, they have developed some so-called homomorphic encryption approach. And this homomorphic encryption, what it does is namely to carry out the mathematic operations based directly on the ciphertext, without to do the decryption at first like here, and then do the mathematical calculation and then encrypt again. So they just do everything so in the cyberspace, based on the ciphertexts. So there was some pioneering work on the encrypted control initiated in 2015 by the group of Cogiso, and they have employed the partially homomorphic encryption approach. The main problem with partially homomorphic encryption is that only part of the mathematical operations can be carried out based on the ciphertexts. So namely, for instance, the pioneer encryption approach can do the addition with ciphertexts, but cannot do the multiplication. And in contrary, so on the contrary, the Algama approach, encryption approach, can do the multiplication based on the ciphertext, but they cannot do the addition. So that means if we employ partially homomorphic encryption, so either there will be much communication node because we need to transform the partial commutation results to the actuator, or you can only protect the signals, you cannot protect the parameters, so that is not indeed what we want. What we want is indeed the fully homomorphic encryption. So the whole fully homomorphic encryption approaches have been developed by Gentry in his dissertation in the year 2009. And so here with this approach, both addition and also multiplication can be carried out based on the ciphertext. The only problem with that is that it needs much computation. And we know that our controllers need to be able to work in real time. So we have only very limited sampling time. So we need to finish all the calculations inside one sampling period. Could be second or could be even millisecond. So how to do that? So it's difficult to apply fully homomorphic encryption approach for our purpose. And so what we have done is that we have checked through the encryption literature, has found out a very interesting approach proposed by Dyer in the year 2019, and it's the so-called somewhat homomorphic encryption approach. It can do both, so addition and multiplication, and it has much reduced computation. Only problem there is that they cannot do it for infinite long horizon. So you must we must think out some approaches to handle with that. So that is what we have done in the year 2020. And so during this procedure, to apply somewhat homomorphic encryption to encrypt our controllers, indeed we have found out something that is quite interesting. So now I have a good news and a bad news. And so we'll tell about the bad news at first, then it cannot get worse. So namely, we have seen that, so even if we have encrypted the signals, so here we have our encryption, we have encrypted the sensor signals, we transmit it over the network, do the calculations in the controller based on ciphertext, and then transform this ciphertext again to the decryption on the other side of the network. But you know that the attacker may also manipulate the ciphertext transmitted over the network. So it is still possible because we have some bit streams with ones and zeros. Attacker can still change some bits of 1 to 0 or change from 0 to 1. And in that case, that means he don't know what the signal values are, but he can still change the value, manipulate the value, and so that we get the wrong signals. And so that is still, so we cannot get the influence out. So that is the bad news. But simultaneously, we get also two good news. The first thing is that if we look at our controller, so here you see at first a very standard process state-space model, and assume that we have a dynamic controller. So you know that state feedback controller or output feedback controller or just some special case of that. So assume that we have a dynamic controller here. So XS is the controller state, and AS, BS, CS, DS, they are the controller parameters. The controller takes the sensor output information, calculates the control input. So now we can indeed rewrite our controller a little bit. So namely, we can write it equivalently in the matrix form. So here you see the matrix F contains all the controller parameters. And in the vector W here, it contains all the signal information. So that means our controller is nothing else than a multiplication of a matrix that contains the controller parameters with a vector that contains the signal information. And so we keep that in mind, and now look at the second good news. So namely here on the left side, we see the standard Dyer encryption scheme. And the key here is that, so at first, standard, it selects some security parameters. In the second step, do the encryption. So here's our message M. And the ciphertext C is called by the message, will be imposed with some noise terms, so that the eavesdroppers cannot read out the true message information. So this theta is a security parameter, and the S is some noise, R is some noise, P is some prime number. Okay, and surely we have some decryption and so on. And my PhD student, so Mr. Fowler here, has found out a very interesting fact. So namely, if now we do a small modification of the encryption scheme of Dyer, so namely we exchange the position of the message M here and the noise S here. So instead of M plus S theta, we have S plus M theta. And then we will have some very desired properties. So here, surely, we need also to do the decryption slightly different than the Euro scheme. And namely, we have achieved the first nice property is that this new scheme, so we have called it as resilient homomorphic encryption approach. So it is namely homomorphic with respect to the multiplication of a matrix with a vector. So that means that is exactly the calculation what we need in our controller, and so we can achieve the homomorphism respect to that. And the second good property is namely shown on this page. So namely, due to this modification, we can achieve some kind of resilience. And why resilience is important? So resilience means that even if, so now our ciphertext is transmitted over the network, assume that the attacker manipulates the signals. So that is the A1K and A2K shown here. So even if the attacks exist, so after the encrypted calculation and after the decryption here, we can still get some correct, not some, but the correct result. Only currently we still have some small limitations, namely we cannot do it really for arbitrary attacks, only if the attack, so this A1 and this A2 here satisfy, so this inequalities here. But the good news is that, so this range, it depends on the security parameter that the attacker indeed doesn't have. So the attacker, it is impossible for them to know where this resilience range is and try to avoid it. So it is not possible for them to do that. So here in summary, if we now encrypt our control systems with the proposed resilient homomorphic encryption approach, we can achieve the resilience. So namely, even if there's some attacks over on the ciphertext, so our controller can still get the correct, our controller calculation results here, it's still correct. So that is the resilience that has been achieved. So now to summarize it up, first thing, cybersecurity of control systems. It is indeed an interdisciplinary research topic, and it involves both control, communication, and computer science. And we have developed some approaches to detect the challenging cyber attacks on control systems. We have made use of our control and for diagnosis pre-knowledge to do that. And the cyber risk analysis shows that there is indeed very realistic potential risk. So even if the attacker doesn't have full access to the signals and doesn't have the full knowledge of the plant model, so the industry really needs to do more to protect their plants. And finally, so the resilient encryption approach can achieve both confidentiality and also the resilience, so namely the integrity of of the data, the sensor output data and the control input data. Okay, so that's the main content. Next steps, we're going to develop resilient controllers, and we're interested in handling large-scale systems. So thank you very much for your attention. You want this one?
Thanks the speaker for the wonderful presentation. Thank you. I'm afraid we don't have time for questions because we need to proceed with the next sessions, parallel sessions, which are starting in 1 minute. So I think we can have time for, if you are around, still around, during also the coffee break, so we can have the chance to ask. But very quick because, oh, now it's working.
Okay, thank you for your presentation. I like to comment that there are a difference between safety and security. Safety is to protect you to any damage, and security is for protect you from another make you harm. Then here we are talking about for security because an attack, cyber attack your information. Then your sensor, one question, your sensor in your plan have IP address? I don't think, because in the plan, all the instrumentation is in a network, local network, Profibus, Modbus or Fieldbus, but it's only in local area. The controller, yes, have an Ethernet port that is connected to the supervisor machine that in many cases, yes, is connected to a router that is connected to internet. For this way, it don't come in the attack. Then if the attack coming from the controller, you don't have to do anything in the control. It's not a control problem. It's a problem of security. You need a guard, a watchdog that detect the problem in telematic way. Is my problem. It's possible when you say that what we can do, we can use safety instrument system. When the safety instrument system is instrumentation, a part of the control system, then the operators can, when the alarm is activated, can detect when there are a problem. It is an important, for example, in the field where the instrumentist can see a manometer or another analog instrumentation. And there are another norms, the International Association of Automation, the 62443, that is hold the norm in cybersecurity in industrial processes. Maybe we can use all this norm for detecting, avoid these problems. This is my opinion, and maybe if you check these norms to adapt to this situation. Thank you.
So thank you very much for your comment and for your questions. So indeed, I work not only in security, but also in safety. So we look at the security for safety systems as well. So I know the difference between safety and security very well. And what you have said was true before, let's say, before 5 years. But currently, you know that, so even the plant owners, for instance, in the chemical industry, they have realized that even though the DCS is very well protected, they cannot avoid the cyber attacks. The reason is very simple. If I sit in my office in the control department of the, let's say, big plant, I can still get access to the data without any problem. I can see all the data. Only I cannot write back directly, but I can read it without problem. So that's why. So nowadays, anyway, what happens in Germany is that in the big providers of chemical plant, they are building up the cybersecurity teams, and just to let us imagine it. So you know that in the cybersecurity teams, they have almost the same number of co-workers as in the Department of Advanced Process Control. So you can imagine that how much they really invest in this field, because nowadays the network is, anyway, the difference between the production network and the office network, it is not so big as before. No? So our plant owners, plant managers, they can get through the, the mobile phone, the information about the plant, and so it is not. And the second thing is that the safety systems are used to cope with critical situations. For instance, temperature is much too high, and so the pressure is much too high, and so on. That means it is already outside the normal process range. No? So it can already cause, for instance, some explosion, some big problems in the plant.
Excuse me.
Why
we need, because we are delaying the next session. Sorry, it's why I didn't want to allow any question, because I know that you are continuing. Sorry to interrupt, but we need to stop this. You can, I'm sorry for it. Thanks again the speaker, and so we can, I'm sorry for it, but we have quite strict schedule, please. The message, 45 minutes for the presentation.
So, any participants in the competition who was planning to present, if you can come up and upload your presentation. If you can do it now, would be good. Otherwise, you can do it when you're supposed to present. So, copy. And then you have it there. Levi's competition, so you just put it there. Okay. 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 Ska stå på scenen då. Jag kan få Daniel med.
My student did it fun, so I will represent by one of group. Yeah. A team. Yeah.
Have you talked to Daniel about it?
I was also a copy that.
Okay, you okay. Okay. So I can start a bit while the participants are uploading the presentations. So I'd like to introduce myself. My name is Daniel Jung. I'm an associate professor at Linköping University, and I'm one of the organizers of this year's competition that we have named the Leo Ice Industrial Fault Diagnosis Benchmark. And I want to thank this SAFEPROCESS conference and the organizers for all the help. And I also want to thank all the participants for their very interesting contributions to the competition. All right, so let's get started. We're a few minutes late, but I think we can manage it. So for those of you who've read the call for this conference, you saw that there was some information about the competition. I just show a picture of our PDF, our flyer, and you can also see the homepage is still accessible if you're interested to look at the data. The session is scheduled as such. So I will start with presenting the benchmark and the motivation for this competition. After that, each participant will have a chance to present their solution. And at the end of this session, we will have a presentation of the results from our evaluations. So our motivation when we designed this competition is that in many of the industrial applications we're working with, we have the problems of deriving a good model is a time-consuming process, and also collecting representative data of all the fault scenarios that we're interested in is either expensive, time-consuming, and sometimes not even possible. So this is something that you need to handle or need to deal with when you design a diagnosis system. So what we wanted to do with this benchmark is to kind of replicate or design a scenario that covers this in both ways. And I will describe how we did that. So the goal here is kind of how can you perform diagnosis when you don't have representative data, or when you don't have some physical insights about the system, but you don't have a perfect model. So we have used one of our test bench. It's an internal combustion engine, comes from a Volvo cars. It's a 4-cylinder gasoline engine. We are focusing on the air path through the engine. You can see it in the schematics here on the slide. So it describes more or less the air flow through the system, including the combustion and so on. Also you see the compressor and gas and turbo. So the available sensors in the system are kind of the standard sensor setup you see in a normal conventional car engine, where we measure pressures, temperatures, air mass flow, and some of the control signals that are available. So more or less there are 10 signals, I think. And what is interesting with the system is that an engine operates in a large operating range. So you have low speed, high speed, low load, high load. So you need to be able to handle this, and you have also these loops in the system. So during the data collection, we have run the engine to follow one of the standard driving cycles that kind of replicates realistic driving scenarios, and it covers both urban driving and highway driving, and a large range of speeds. And so this is kind of to be as realistic as possible. Data has been logged in 20 hertz. You can see some example here on the lower plots here how this data could look like. So to create faulty data, we have ability to inject faults directly into the control unit by modifying the control signals. So we've injected sensor faults in this way by multiplying the measured value with some error. We also have created leakages or leakage by having a valve that we can open and close to control the kind of the size of the leakage. So the resources that we provided for the participants is one is I would say state-of-the-art mathematical model derived for the system, but we don't provide any parameters, so only the model structure, and it was implemented in the fault diagnosis toolbox. We also provided 8 data sets, 1 fault-free and 7 data sets with faults. So each data set represents one of these driving cycles I showed in the previous slide. And it's about 30 minutes data per data set. In the faulty scenarios, we introduce the fault after 2 minutes. So there is an initial fault-free section, and then the fault is introduced. And the table down here represents kind of a summary of what type of faults that is provided in the training data. So as you see that these -10 plus 10% is kind of how much we multiply or kind of change the true sensor value in the control system. And for the leakage, we have an orifice of a diameter of 6 millimeters. And we also provide a code structure that to how the system should be implemented, that it could be done in both MATLAB and Python. And the structure kind of looks like this, just to give a feeling. So the diagnostic system was supposed to be implemented as a class. And for each time instance, you get a sample, and you should return, have you detected a fault or not? And if you detected a fault, you should rank any of these fault scenarios. And we have looked at 3 sensor faults and 1 leakage, and you can also set a ranking of an unknown fault. So you want to rank these based on which one you believe is the most likely one. So for the evaluation, we have set up a set of criteria. We have mainly focused here on false alarm rate, misdetection rate, fault isolation accuracy. And some of these aspects like computation time, we have looked into that. I will show some results later. But because of implementation issues, we haven't really been, we haven't seen this. We have looked at it, but we haven't used it hard in the evaluation. So before the presentations, I would like to present the 6 participants, and they will present their solutions in this order. So we have 6 participants, 1 group from Warsaw, 1 from Bergamo, 2 participants from Central South University in China, and then there is 1 team which is from several universities, University of Calabria, Islamic Azad University, and Polytechnic University of Catalonia. And the last team is here from University of Victoria. So I would like to welcome the first contributor, so Anna Streiber. Can please come up and present your solution. So the plan is to have like 15 minutes, including questions, if anyone is interested.
Oh, thank you. Okay, hello, my name is Anna Sztyber. I'm from Warsaw University of Technology, and I will present my solution to the benchmark. First of all, I would like to thank the organizers. It was actually a lot of fun to participate, and I think I now have some interesting research question to dive into. And also a special thanks for Daniel for being super helpful and responsive. Okay, I will start with what I tried and what didn't actually work, then I will show you what I ended up doing, and then I will complain a bit more about what didn't work. So my initial idea was to use the nominal data as much as I can, because in most cases we don't have data from the faulty states. So I wanted to start with some structural approaches. The first one was the obvious one, like the structural model that we have in a fault diagnosis toolbox. And then I tried graph of a process, which is a causal graph for finding partial models in the form out equals the function of inputs. So, and for these 2 methods, what I wanted to get was actually get the model structure and also the fault sensitivity, and then fit the actual model with the nominal data. I failed completely. I will go into that more. And some other ideas that I tried, it was to use autoencoder, and also my colleague, Maciej Przybylski, he played a bit with classifier, with KNN distances, but finally he did not decided to submit the solution. Okay, so what I ended up doing, the solution is named Kerr engine, classification residual analysis for engine diagnosis.
And what I did was, first I used handcrafted residuals, then I computed diagnosis signals with adaptive thresholds, and I used two separate classifiers, one for detection and one for isolation. So I will come back to that later, but first complaining. So what I started was using MSOs and fault diagnosis toolbox. And so what I did, I computed all MSOs, filtered the one with low index, and computed the fault sensitivities and the measurements. And to my surprise, there was the case that you can actually get the MSOs with the exact same set of the measurements, but with different fault sensitivity. And here is a small example for temperature in the intercooler. So for these two MSOs, we have a different computations path that give us different fault sensitivity, but it's actually a big problem if I want to estimate the model using the data. And here, I just want to take a second to appreciate this strangeness. So we have two residual generators that we have exactly the same set of input signals. We have the same residual, like we are estimating the temperature in the intercooler, but we have, like the residual generators are big, but we have a small difference in a few equations, and what it results, like the theoretical fault sensitivity is actually different for these examples. So at this point, I gave up with that approach. So I was thinking, okay, I have my own graph of a process approach, and with this, well, at least I avoid this confusion. So I have input-output models, and I have like one fault sensitivity for this. So what I did, I designed a causal model, and I did it actually from the equations. So what I did was like the right-hand side variables influence the left-hand side variables, and I used integral causality. But what was the result? The result was that actually all the model structures were sensitive to all the faults. And this is possibly quite true because like the system is actually one big feedback loop, so like everything is influencing everything. But does it help me with fault isolation? Not at all. So I also gave up on that. So what I end up with doing is actually I designed the residuals by hand, and they were just partial model. Here we can have a look at what was the output, input, and I have 3 types of models, 2 neural networks and 1 linear, and I did a bit by experimenting and also by looking at the description of the engine and how the system is working. My impression was that the biggest problem with the competition was we actually overfitting to the training data. So here I tried to be as simple as possible. The models are really small, and they are all trained on only the nominal value, no faults here. So I have 3 types of models. One is linear. It's rich regression with L2 regularization. Second model is neural 1. It's neural network with 1 hidden layer with 8 neurons, Adam optimizer, ReLU activation, and also with L2 regularization. And the neural 2 is the same, but we have 2 layers with 8 neurons. All these models are static and actually quite small. A little remark about temperatures. So I tried to make a modeling intercooler temperature, but I was not quite successful with that. And also there were 2 variables, ambient pressure and ambient temperature, which did not have enough excitation in the data, so finally I decided to not use it at all. Okay, example, residual R1. This is actually a model of the intercooler pressure, and here you have input variables. And here is a plot with the model output and the real value. Model output is in orange. And here you can see a residual. It basically works, but you can observe that during the dynamic conditions, the fit is actually worse. Okay, so to avoid false alarms in the more dynamic situation, what I did, I used adaptive thresholding. So I actually fitted linear model, like the function of the residual depending on the value of the modeled variable. And this is like linear model in segments, and I have bounds that are the expected value of the residual plus minus 2 standard deviation. And also like the lower bound is always less or equal to 0. And here you have an example of those bands. And with data with fault, we can see that actually when we start without the fault, like the model is more or less where the data is. And when the fault occurs, like the model is actually quite diverging from the real data. Here is the residual, and you can here see the residual with the bounds. So, okay, this example is a bit cherry-picked, but this is one that is working nicely. So we have the signal outside the bands. Okay. At this point, I decided, okay, I should actually use the faulty data. So I just made classification based on these diagnosis signals and residuals. So I had 2 separate classifiers. First one is for detection. So for the detection, I used quadratic discriminant analysis, and this was made on the diagnostic signals. So this was after thresholding to be more robust, I would say, for the false alarms. And the signals were revalued, like it was 1 if the residual was greater than the upper threshold, and -1 if it was lower than the lower threshold. And also, I did some exponential averaging to avoid fluctuations. And the isolation classifier was linear support vector classifiers. And to actually transform the space of the signals, I use a Neostrom feature transformation. And features here were residuals, averaging was the same. Okay, unknown faults. For the isolation, I used linear SVC. And this classifier, I had 4 known faults. So I had actually, as the output of the classifier, I have 4 numbers. And if the output of the classifier is greater than 0, so the classifier is saying that this is actually the probable class. And if it's lower than 0, it says not. So actually did some kind of trick, just like I appended 0 to the classification results and then computed softmax. So in that case, like actually if this SVC classifier is predicting a class, so I take it, but the unknown fault is like on the 0 position. Okay, some analysis of the residual space. So here I made T-SNE projection of the residual space. And we can observe that some faults can be easily isolated in that case. For example, here we have the orange one, which is a pressure sensor fault. And also this one are clear, but we have a problem. I had a problem actually with no fault state and the fault in the air mass flow sensor. So like this was the most difficult for me to actually detect and isolate. And what I also found challenging, because I wanted to tune the parameter of the classifiers, type of classifiers, averaging thresholds, signals that I used. And actually it was quite challenging to find a reasonable validation set, because the evaluation was supposed to be on different data. So what I did, I actually split the data in the temporal order and took the first 80% for training, and the last 20% just for the validation to tune the parameters. And like, this is what I got for this validation. What I'm actually interested is how it transferred to the unknown data. And we can also observe, like here is also the percent of unclassified data, and this is the result from this trick in the SVC classifier. So we have some, like the samples that are not classified are actually the unknown fault, and we've also, you can see that we have quite a significant percent for that, even for this validation set. Okay, conclusions. So I have not found a reasonable way to use fault diagnosis toolbox and MSOs or graph over process. I think that the pressure sensor faults are much easier than any other kind of faults for this system. It is a challenge to estimate the performance on the other cycles and other faults. And some of the difficulties result of the feedback in the system. And actually it would be interesting because the engine has a control system, and probably there is some knowledge about the structure of the control system, control signals, set points, and so on. It would be actually interesting to have it in the data and include it in the diagnosis system. Okay, that's all from me.
Sorry. Okay, so thank you for your presentation. It was very interesting to hear your story, kind of how to approach the problem. I think we have time for one quick question. Otherwise, we can take the discussions afterwards. I know we have a tight schedule, but this room will not be occupied after this session, so if people want to discuss more, we can stay here and talk more. Is there anything now someone want to ask? No? Okay, thank you. So I would like to welcome the next speaker. So it's the Italian team. So it's Nicolas Anselmi. No. Yeah, Francesco Corini. Yes. So the stage is yours.
So, thank you very much. I'm Francesco Corrini. I'm from University of Bergamo. I'm a master degree student in IT engineering, and no, it's not working, so I will use the arrows. So we are presenting our solution for the competition. With me worked Nicolas Anselmi and Andrea Ricci, two colleagues of mine, and Professor Mirko Mazzoleni. And our solution is based on adaptive squares as a residual generator and open set classification techniques for fault classification. So before training our models, we did some data pre-processing. We filtered our data with a cut frequency of 1 Hertz to remove some noise. Then we organized the data in features, like basically many times will be variables, but sometimes will be square, log, or interaction between two variables. And then we standardized these features using the standard deviation and the mean according to the feature computed on the no-fault dataset. So let's discuss about the residual generator. It will be adaptive square. I think all of you know adaptive squares. Yes, we have a linear time-varying model. We estimate it using this cost function, minimizing this cost function with this forgetting factor, which penalizes more the error on newer data than past data. But the great thing of this model is that we can estimate the parameters recursively, so in a very efficient way to do in an online system. So the structure of the residual generator would be 4 adaptive square models, and the residual sequence will be not the prediction of the models, but actually the parameters, the time-varying parameters of the models. And in fact, we will select 2 parameters from each model and do classification using them. So the first model is used for detection of the peak fault. And it is this structure, so the intercooler pressure is predicted using the throttle angle and the throttle angle squared, and the forgetting factor of 0.999. We select the parameters 0 and 2, and what we can see, computing the residuals on the no-fault dataset and the peak 10% fault dataset, we can see that after the fault occurs, of course, there is some overlapping in the first data where the fault is not already in the data, but when the fault occurs, the parameter separates, and so we can easily classify when there is a fault or not. But the very important thing is that on other datasets, like I take the airflow, but I could take also other datasets, then the residual does not separate. So we can use this type of, this set of residuals to only isolate the peak fault. But actually to create, we will see next, a robust classifier, we can use 6 datasets, not only one, to train the nominal region, the blue region, where there is no fault, there is not the peak fault, and we can see it in this slide. So the blue region is not computed only on the no-fault dataset, but on all 6 datasets that doesn't contain the peak fault. And instead, we can see when we have minus 10% and plus 10% fault that they separate, and also they separate nice because they separate in different places of the plane, in the opposite. So there is some consistency in our residual. We did a similar thing with the pin fault for detecting the pin fault. We have this model. We predict the injected fluid mass using the intake manifold pressure squared and the engine speed. We use a slower forgetting factor than before, and we select the parameters 0 and 1. And here we have a similar results. We can see the nominal region computed on 5 datasets, and here the faults that makes this residual react are free because also the leakage, which is in the intake manifold, and since in the model we had the intake manifold pressure, sometimes it also reacts to that fault and not only to the pin fault. So this is an undesired behavior, but we will see that we managed to find a solution to not have misclassification later. Here we can see also the consistency when the GIF go on, that the pin fault with higher magnitude separates better than the lower magnitude to the nominal region. We have another model for the airflow. This is a more complex model. So we predict the injected fluid mass using this strange feature, which is the logarithm of the engine speed multiplied by the airflow, then only the airflow, and then throttle angle. This slide is wrong, I forgot to update, but let's see the graphics, that is better. And so we can see this time that we have the nominal region, we have the true false plus 5 and plus 10% that separates, but also the leakage separates, but this time it separates really well. So we can use this model to detect both faults, but in some way we need something to distinguish between them. So what we done is to create a fourth model that will react only to the leakage and not to the airflow fault, to the sensor fault of the airflow. And so this is the model. To go faster, we only observe that we have the nominal region, and when the leakage fault occurs, it separates. So to see that in a complete view, when there is no fault, we can see the nominal region estimated on all the no-fault datasets, so the one which has not the fault inside, not only the no-fault itself. And we can see, using the no-fault dataset as a test dataset, so removing them from the blue region, we can see that it overlaps really well. So we can say that there is no fault. When there is a peak fault, only the first residuals react, so we can classify a peak fault. When you have a pin fault, only the second reacts. When you have the airflow, only the third. And when we have the leakage, the third and the fourth, and sometimes the second model. So what we can do is to create a classification logic which takes into account what we have just seen. So we have no fault when no non-residual reacts, but we actually, for robustness, doesn't consider the last residual, which we use that only to separate the sensor flow of the airflow and the leakage. And so there are all the other patterns that we already seen. And in the leakage fault, we don't consider the second residual because sometimes reacts, sometimes not. So we decided not to consider that to make this classification. So now, we see we can do classification here, but we need a classification algorithm. What we decide to do is to use an open set classification method described as in this paper of Lundgren and Daniel Jung, which is here. And the idea is to take a time series of the residuals, divide that in batches, estimate the probability distribution function of these batches that characterize the nominal region, the blue region that we saw before. And so producing a one-class classifier that tells us, are you in a nominal region or not? So here we explain better the idea. We divide the time series of the residuals in batches of size, in this work, 300. And we compute on every batch a probability distribution function. Since we are assuming the PDFs are normal, then we just have to compute the mean and the standard deviation of the sample. And so we will have, having 4 sets of residuals, we have 4 classifiers, and so 4 sets of distribution estimated in this way. And we will call these train sets. So when online data are collected to make classification, we collect some data to produce a new batch, train a new distribution on this batch, estimate a new distribution on this batch, and then compute a measure of the similarity of this distribution to the distribution in the train set. And if this similarity is under a certain threshold, then we can say that the distribution is inside the set of the nominal distribution. So basically there is no fault. To compute this similarity, it is proposed in the paper to use the Kullback-Leibler divergence, KLD. And if the distribution are normal, as we assumed, we can estimate this similarity in a closed form. Actually, in our work, we use a derivation of this formula that uses Cholesky factorization to speed up the computational process. And so, given two distribution, we can compute this similarity. And to compute the similarity of the distribution respect to the set, the train set, we just take the minimum similarity between the two sets. And so, which is the closest we can say distribution to the one we estimated online, then that's the distance to the entire set. How we can compute the threshold? So train a threshold that is good for our classifier. We take a distribution inside the train set, and we actually compute the distance between all the other distribution in the set. Doing this for each distribution inside the set, we can say we have a distribution of the distance, and using a kernel destination approach, we can compute the cumulative distribution function, and we will take the 99th percentile of the quantile of the percentile is the same thing. And so the quantile will be the threshold. And so when the distance of the online PDF, the distribution estimated online is lower than this threshold, we can say the residual is in the nominal region of this set. And so basically train 4 classifiers like this on the residual we saw before, we can do classification. And so we can discuss a little bit the validation result. These are doing with a leave one dataset out cross validation, because basically we trained the diagnosis system with 7 datasets and test the performance on the one which is left out. And so we can see we have 91% of correct classification rate on the no-fault dataset with 9% of false positive. Instead, with the classification, when there is a fault, we have approximately 90% of performance of correct classification on each one. Then sometimes we detect the fault, like 5%, but we doesn't isolate it correctly, and instead the misdetection rate is very low, and it's basically only here on the dataset with only 5% of magnitude. That is, so having a fault with low magnitude is it's harder to detect presentation. Thank you. Hopefully I don't went too long. So.
So thank you very much. Is there anyone who wants to ask a question? Yes.
So could you go back to one of your residual slides?
Residuals, which one?
Yeah, back. Yeah, this one. Okay. So first of all, I have to thank you because I never experienced fault detection as art, so this is really nice. Now to the question, if you probably go one slide back, no more, yeah. On this, yeah, next one. Okay. No, back. Here on your basis function, can you comment on how you converge to these basis function for the regression model? On how many parameters you need there and how many?
No, which basis functions?
I mean the models, right?
So this is a linear model.
Yeah.
The X are features, so are computed using the...
Yeah. The question is more like, how did you converge to exactly that model? I mean, you can add terms, you can reduce terms.
Basically, I look a little bit on the structure of the model of the system. I looked at how the variables we had interact by themselves, and so we tried to have models that have. So I didn't use an algorithm to select the model or doing like validation to have the lowest possible model. Instead,
so a little bit of trial and error.
Yeah.
Okay, thanks.
Can I have a follow-up question?
Yeah.
How many attempts did you make before you?
It depends. The peak model was like 5 minutes. I had this model because it was really easy to separate the fault between the nominal region. Instead, for the airflow, which is the challenges, the most challenging also in the paper of Professor Jung, which has the lowest classification score. This take like weeks of trying. Of course, not entire time, but to think how I can extract some meaningful information from the data we had.
Okay, so thank you very much. So I would like to welcome the third group, Yamin Shu, I think. Or, oh, perfect.
Yeah.
You're quick. That's good. Okay. So the stage is yours.
So where's the
pointer because it was disconnected. The pointer.
Sorry.
Because
So
it's
that's
disconnected.
Better. That's better. Yeah. Thank you.
Could you send me the complete names of the people who asked us for a report of everything of the conference? And I think this would be good to the name. Say about the winner.
So, can I start?
Yes, go ahead.
Okay, hello everyone. So my name is Jibin Chen. So I'm the instructor of this. This is joint work of my student. So it's an interesting benchmark competition. So because due to the visa vision, I just represent my theme. Okay. So we give a solution about named data-driven distribution matching method with application to. Excuse me. Motivated by this work of the. Okay, so I would like to present in the following 4 aspects. The first is the background, but I will go quickly because Daniel have give a nice about the background. Okay, so this is the complete objective. So we design a diagnosis, but especially so we don't have some many and the model information about this this engine. So the only given us the data. So, and also we analyze this because previously we used the structure analysis to some the fault density work, but it's good. But in this task, so the parameter theta is missing. So, but this information give us some variables and of the fault signal and the knowledge and the known signal, and also help us to analyze this task. Okay. So based on the difficulty of applying the model-based methods, so we choose the data-driven approaches. Okay. So, and this is the structure because actually, so in this data set, so they provide the 8 sensors and 2 actuators, but we don't use all the variables because some variables are not sensitive to the fault. I mean, there's less correlation with the kind of fault. So I just make a simple variable selection. So, okay. So because this is the, we take the airflow in and say, pass each component, we go out. And here is the 8 sensor signals and 2 actuator signals. Okay. So we also do some data analysis, and because we have measurement noise. Okay, you can see this figure, and also we have we just draw the distribution, but it's we see that. So the distribution information is different, and with every left, this is the air miles flow, and this is the engine speed. And also, we just encounter problems that we have limited training data. Yeah, so that means that some methods and heavily depends or rely on the data, the number of the size of the training data is not available. Okay, about that. So because each type of fault has only one set of data with a length of 30 minutes is, I don't know it's long or short, but I think it's not enough. Okay. So, but the fourth is unknown fault issue, because this is quite interesting, but still challenge. Okay, because what I understand the unknown fault means that because here maybe we have some information about fault. It's not totally new because it's only we didn't see it, but we have some information about it. But the organizer didn't provide us such information. So for us, so this also is unknown. Yeah. Okay. So because based on this observation, so we choose the distribution-based method. Okay, it's also a very well accepted approach, but we also made some modification on that. And also, this is our evaluation. So because we have a measurement noise, but we can ignore the internal trend of the data changes, and also we assume that the noise have the zero mean, which means that the noise does not affect the mean of the distribution. So mean is also the kind of feature of the data. And also because we're adjusting the sliding stepper to change the amount of distributions on a large scale. So these features we can apply to deal with the limited training data. And also we identified unknown fault by comparing the data distribution. Even we do not have much information about unknown fault, but we can still assume that they have a different the distribution information. So we can also follow this logic to deal with some unknown fault. Okay, so that's is the 3 aspects why we use the distribution to do this task. Okay, and also this is the fault scenarios provided, and this is the evaluation matrix. So I think so this matrix is very good because usually we only focus on some of the fast alarm rate or the miss detection rate, but we didn't consider more about computation time, because this is also constraint some that's also towards the high fidelity the data the approach, because in practice we often need to consider the computation sources consumed by our approach. This is very important. So I think so it's also a motivation also motivated us to select this method. Okay. And the next, I would like to introduce this method. So this method, the structure of the proposed method includes the data pre-processing and next sliding window and the technique, and also we assume that because we don't have more information about that, we just assume that it follows Gaussian distribution. But because we also see that evaluation metrics have the computation time. So this also why we choose the Gaussian distribution, because it can parameters by two parameters. One is the mean and one is the covariance. So that's, we just assume that it follows Gaussian. And we do some of the labeling and also calculate the threshold. Okay, so that's, we get that. So at the first step, so we have, we compute the min max normalization of the input data, because this, we can just narrow the data in a more normalized range about that. And also we just, because this, the estimation of the mean value and the covariance matrix is quite standard, but it's useful because this is only, you can treat this as a feature. I also noticed that previously some candidates also introduced the residual signal, but it's also kind of features in my mind. Okay, so here we only focus on the mean and also the covariance. Okay, and also the cross covariance about that. And the next we use the Kullback Leibler divergence to compare the kind of distance between the distributions. Okay, because we have because the organizer provide us some the data, we call it historic data, and we can estimate some of the candidate distributions using these data sets, and we storage it. And so and the same we use this because this is also quite standard. I just ignore that. So and we determine the threshold based on the divergence matrix. So this is really a challenge. It's more based on the experience. We don't have because we have in each because we have different estimated number of distributions on each fault data set. But we just determine the threshold and just select it as the top 1% of the value. So we ask the threshold for according to each fault scenarios. The I means the each the fault scenarios. Okay. And here in this step, we calculate the KO divergence between the Gaussian distribution of test data. Because if it's Gaussian distribution, the KO divergence is quite easy. Okay, because but we don't have any. We don't make any assumption about the mean or the covariance matrix, so we need to use the mean information and the covariance matrix when we calculate the KO divergence. Okay, and also we make make a decision logic, and also we have a decision logic for the unknown fault, because if the estimated distribution and close to the historical distribution, so which means that KO divergence will be small. But if the KO divergence is bigger, so we think that they are the different fault or different situations. So because if all the KO divergence big than beyond the thresholds, so we could say, okay, this data is possibly from the unknown fault, okay, because it didn't close to any historical fault scenarios, okay, and also the normal scenario. Okay, so a single data set's fault categories self-determined and potentially influenced by outliers and causing significant fluctuations, so that the next we also have figured out a way, because we call the Monte Carlo based historical data fusion, because we want to just solve the above issues. So here it's also we use the KO and we estimate it, and also the R we call the forgetting coefficient, and also the square. We only just take this one. And also we collect the broad information to make diagnostic decisions and improve the reception fields. And also, yeah, we call this reception fields, which means that it's just similar to the convolutional neural network, but it's a similar idea, okay. So here we reduce the sudden changes in the fault types to better match the actual situation. And so we will do some an offline experiment to validate this method. And this is we just draw the original curve about the sensors. And this is the hyperparameters we decided because try and error. So, and the window size we selected as 50, okay. So the step size in training sets is also 50, and the step size in the testing sets is same, okay. Also, the selection criterion for the thresholds, we just on the top 1%, okay. So the principle of selection is the size of the window and the step influence the number of the feature, distributes lambda for various faults, and a small window size leads to distributions that do not adequately reflect the train's temporal data. So this kind of parameter, so we also do lots of try and error. So because I don't have any like some mathematical about that, we try and error is good. Okay, so and here is the bar chart of the distribution, because in the normal in the fault-free data set we estimated almost 5,000 distributions, we call that. We just stored it. And if we have, this is for the different fault scenarios, we have, we just make this and distributions. But when we do validation, so this is quite, cost a very large computation time. So we only think it out at a trick, because we can just construct this as a matrix. And the same way for the online matching. So we just do the matrix and the vector multiply. So that's, it's much better, faster than with the original, so the methods, okay? So the bar chart of the threshold for various types of faults, the normal free, we choose the near the 12, and with this second, but different values. Okay, the obtained distribution are used for fault diagnosis are internal. Okay, this is also we visualize the mean distribution of the different scenarios, okay. And so this is the how to calculate and this is the, we just run on this server in our lab, okay. And also, this is our results based on the validation data. But because of the final results, we didn't know about that. Okay, that's only for yes, for a reference. Okay, and this is some the visualization about that set. This is the because this is different step size, and this is have a good result. Okay. And this is a visualization about unknown fault. So because we can see that every scenario we have the chaos divergence is big than beyond the threshold. So we mean that this is very quite is not familiar with the fault we know. So this we just decide as the unknown fault. Okay. Okay, so the summary. So it is the brief summary because the time is approaching. So I just quit because the experience corresponding forgetting of coefficient to the chaos divergence for each W is utilized, and also we do some the effectiveness of the proposed method. It's also get some very good results. Okay, so thank you, yeah, for your attention.
So thank you very much. I think we have to continue with the next speaker to keep with the schedule, but I hope that you have questions for later. So I would like to welcome the next speaker. Yes, I'm going to. So it's maybe.
Okay, my name is Mehdi Purzanfer, and today I want to discussing about our purpose solution about industrial fault diagnosis benchmark competition entitled Anomaly Detection and Fault Isolation with Incomplete Data. This report authored by my colleagues, me, Hossein Safaipur, Vahid Mirahi, Anna Pinarelli, Vicent Puig from the Islamic Azad University of in Iran, and the University of Calabria, and the Polytechnic University of Catalonia, Barcelona. Okay, because the other competitor talk about the framework of the competition, I jump from this part and focus on the purpose solution, and after that talking about the simulation result and summary of the innovative result. Okay, our solution, for solution strategy, we decided to working on 3 different paths. We're working on the deep learning, stochastic analysis using PDF, and ANFIS that we consider for this competition. After evaluating this approach, we finally decide to working on the ANFIS because of our background in this process. The operation modeling is the first part of our solution path. We're working on the ANFIS to model different faults and healthy model of the system. After that, online monitoring, residual generation, and fault diagnosis is our challenges in this competition. First of all, we divided our procedure into different parts, modeling and fault diagnosis. In modeling, we're using the usual data processing and some tricky options for that. And after that, for offline modeling and threshold selection. And after that, we go to the next part of our solution. It's related to the fault diagnosis for online anomaly detection. After anomaly detection, it's triggered the next part as for fault isolation. In the sub part of the modeling, we're using the different and usual data processing procedure. We're using the capture data. After that, go to the next part for the feature selection. This is a challengeable part of the solution because we should remove many of data, unnecessary data for each models. For this, that we using some mathematical solutions and tools to remove some unnecessary parameters. And finally, for each of the faults, we consider some effective parameters. The next was related to the model training. We're using ANFIS modeling MATLAB tools for this part. We generated 4 faulty models for this competition, and also a healthy model for the operating mode of the system. Next, we have a big challenge, same as the other competitor, for the residual generation. Usually, we're using the filtering in the part of the capturing the data, but at the moment, we're working on the residual generation because we have a new challenge that we have no complete data set. So we're working on the residual and consider some filtering for that. If you see that we have 2 residual signal generation for the healthy because some faults is sensitive to one residual, and one fault is WAF is sensitive to another residual generation. So we're using this. The residual filtering is another part of our procedure, solution procedure. we using different but simple filtering methods for the residual to remove the noise, uncertainty, and other things. As you know that the residual generation as a equation 1 is the usual equation for generating the residuals, but we're using some mathematical, statistical, and signal processing tricks to generate and filtering the more clear residual signals. And the second one, if the first one is not sensitive to a fault and we need the second signal, by this equation, it's an innovation of our procedure. We're working on the standard deviation and using the energy of the signal instead of the usual residual signals. And for that, we have two residual signals, Ri and R bar I, both of them using for anomaly detection, Ri using for peak, PIM, and IML, and R bar I is just used for WAF faults. And the last one in the modeling part is in the data processing. If the is the threshold selection, because we have no any information about the other data set that we should using in the future. We have a problem to tuning the threshold selection. So we're using a robust threshold selection and evaluation by using H infinity norm and easily adaptive, make it adaptive for our solutions. The next main part of the solution is the online anomaly detection and online fault detection. In online anomaly detection, we have online anomaly detection for the 4 faults and also 1 unknown faults. We have 2 distinct detecting residual, as I described it in the previous slides. And we have innovation in detection logic. In our detection logic, we have adaptive but simple and mathematical based criteria for the evaluation of the anomaly. It's related to the counter of the occurrence and detecting the faults. And if it's not touched, we have another logic to reset the counter and again do this up to detect the anomaly. The next part is related to the online fault isolation. After that, we detect the anomaly. We go, this part is triggered, and the online monitoring, data normalization, and similar that logic we're using in the previous sessions for anomaly detection. We have the similar strategy and logic for fault isolation. Our result is based on the provided data is not bad, but also some good. We have anomaly detection and fault isolation. The fault isolation time is not considered in this competition, but we write it. Maybe it is very useful for the real practical procedures. And the simulation time, the best one is for the no fault is clear, and the WAF is the simulus, and the worst one is the peak 090. If I want to summarize our solution, we can say that we're using the ANFIS finally to determine the NGR operating modes, healthy or faulty. We have some innovation for feature selection and optimization for computational time accuracy. If you also remove some of these criteria, you can change the results. For example, if you remove the criteria as a computational time or fault detection, the result could be changed because some parameters can be changed and the conservative will be changing your procedures. Finally, after we using our models and testing our models with this data, we have no false detection, we have no misdetection, we have a precise isolation accuracy and competitive detection and isolation time, as we know, but it's depend on the others. Thank you for your time and kindly attention. Thank you.
Thank you very much. There is time for questions, if anyone wants. Okay, so I thank the speaker again. So now for the next group. So your name is? So? Yeah, so Chowdhury will present the fifth contribution.
Good afternoon, everyone. I'm Chowdhury, a doctoral candidate from Central South University. I'm honored to participate in this competition and present our work. The topic of our work is canonical correlation guided deep neural network with application to photo diagnosis. The first part is the background. Internal combustion engines are crucial component of automobile. Long-term working in extremely harsh environments such as high temperature, high pressure, high speed, and strong vibration, these engines often have malfunctions. Diagnosis this fault is important for safe and efficient operation. The engine operator in four stages: air intake, combustion, power, and exhaust. The air pass covers the entire journey of the air from entering the engine and combustion and then release. The objective of the competition is to design a diagnosis method for the air pass of an internal combustion engine to address the challenges as follows, such as strong coupling, dynamic nonlinear behavior, only data set available, and unknown fault, and measurement noise. The available information is as follows. The unknown faults include intake manifold leaks, airflow sensor faults, intake manifold pressure sensor faults, and intercooler pressure sensor faults. The complete diagnosis system solution will be evaluated based on the following criteria, such as FAR, MDR. Next part is the task analysis. The airpass systems have many parts and complex process. It provided 8 sensors and 2 actuator signals. The location of the sensors are shown in this figure. there is a strong correlation and coupling among various signals in the AirPass systems, specifically the correlation between the YPM, YPM, UMF, and between YTIC and UTAMB reached 0.4. Additionally, lack of physical model, only data set available, and the data has dynamic nonlinear behavior. Therefore, a new fault diagnosis method for internal combustion that can address this feature is needed. The third part is the CCDN-based method. The motivation of our method is deep CCA, which was proposed by Galen in 2030. The goal of deep CCA is to improve the correlation between different data views. However, because the method has multiple optimization objectives, there are no unique solutions, and the model training step of deep CCA are time-consuming, and the fixed network framework is not suitable for diagnosis task. Therefore, in order to solve the above drawback and motivated by deep CCA, a novel CCDN method is proposed. Then, I introduce the structure of CCDN method. Firstly, the input data of the device is treated as view1 data U, and the output data is regarded as view2 data Y. Data V. Next, the dynamic nonlinear filter Z1 and Z2 contained in the two data view and extracted by two convolutional neural network. Moreover, according to the linear canonical correlation principle, a redundancy filter is developed to reduce the strong coupling between the sensor variables, obtain the residual signals R1 and R2. Both residual signals are connected and input to the fault connection layer and the softmax function. The one-hot predictor for the label is obtained. Lastly, by minimize the cross-entropy loss function, the fault diagnosis method accuracy of the network is improved. In summary, our method can use different models to achieve four functions, including training a correlation unknown faults aware, redundancy reduction, and correlated expectation learning. The first part is experimental study. The selection of variables greatly affects the experimental results. Before training the model, we selected variables carefully. Since some variables are easily affected by the environment, we choose the sixth variable circled in left figure. We then did further variables selection experiments. From the correlation matrix, we saw the four variables YPIC, YPM, YWF, and y-expose has strong correlation. To maximize the correlation between VO1 and VO2, we assign these variables to VO1 and VO2 respectively. Experiments show that this combination gives the best results. We detect 4 types of the faults and evaluate the results using the computation cumulation formula. For this data set with different fault level, we calculate a weight average. As shown in this table, our method efficiently isolates various faults and has a faster computation time. Additionally, our method has 2 extra advantages. Firstly, the proposed method can diagnose faults of varying different fault levels with the same type. Secondly, the CCDN method has a faster computation speed compared to the traditional deep CCA. Handling the unknown faults is as follows. We saw that the network probability output of the unknown faults often gives similar probabilities for several classes. So we set the threshold around 0.5. We did an experiment training the model on 7 types of the faults and simulating WF110 as the unknown faults. The method successfully isolated the unknown fault samples. The next is the summary. Overall, facing the exciting challenges, the proposed CCDN method can use CN to extract dynamic nonlinear filters and redundancy filter to reduce strong coupling between different sensor variables. Additionally, the probability value of the network output can be used to detect the unknown faults. Compared with the traditional deep CCA method, we introduced the signal objective optimization and signal training step to speed up the training process. That's all. Thank you for listening.
Thank you very much. Do we have any questions from the audience? Yes?
Thanks for the interesting work. I just have one question regarding the fault code. You have left, I think, 5 or 6 fault code there, right? Yeah, yes, here. So the fault symbol you mentioned 01 and Y for this pressure sensor fault, and manifold pressure sensor use 2 and 3, and another one 4 and 5.
This example we can ask this the 7 faults.
8 faults, not 7. You have 0 to 7. So that means 8 modes, right? Yeah.
Yeah.
But my question is why you don't use either 2 or 3, but why you use the both 2 and 3 as one fault mode here. Yeah, because it's same fault mode, you can use only 2 or 3. So for 2 and 3 represent a different magnitude for the same sensor fault, right? Okay. Thank you.
Any more questions? Otherwise, thank you for your presentation.
Thank you.
So I would like to welcome the last presentation, the last contribution. So it's Silke Merkelbach. So the stage is yours.
Okay, welcome from my side as well. I'm presenting the results of Mayam and me. Mayam is working at the University of Victoria in Canada, and I'm working at the Fraunhofer Institute in Paderborn, so it's a German-Canadian collaboration. So let's come to an overview of our solution. We developed a purely data-driven approach, so we didn't use the physical model. We tried to, but we had similar problems as in the first presentation, and since there were no parameters, we didn't know how to use it. In our solution, we considered each time step independently, and in total, we used 2 variational autoencoders and 1 support vector machine. Here you can see an overview of the solution. 1 variational autoencoder is used for fault detection to see if there is a fault. The second variational autoencoder is used for fault classification to see which of the known faults could it be. And the support vector machine is used for unknown fault identification to see if there's an unknown fault or if the faults are known. So let's come to the training process. The data processing was done like that we used for the fault data everything above 130 seconds to make sure that if there are, the faults were injected at 120 seconds, and if they were not completely exactly at this time, then we said, okay, 10 seconds margin to be sure. And the no fault data was used the time before 110 seconds and the complete no fault data set. We also added noise to make the model hopefully more robust, applied a scaler, and used 70% of the data for training. The architectures of the 2 variational autoencoders are the same and shown in the top area of the slide, and the support vector machine is shown below. So let's come to the variational autoencoders. Let's start with the first one. For the fault detection, we used all data and had a binary classification, which you can see at the right, between fault and no fault. So our encoder takes all the 10 values as input, all the 10 sensor signals, and we have 2 dense layers, one with 64 and one with 32 neurons. We tried a little bit to have less and more, but after hyperparameter tuning, this seemed to be the best combination. In the middle, we also have the Kalbeck-Leibler divergence in the loss function. So I think we are the 3rd or the 4th using this. Seems to be a good approach. And the decoder is mirrored from the encoder. So in the latent space, there are 60 neurons, or the input layer is 60 neurons large, and again, 32 and 64, the output is 10. We also have a classifier down here, which has 8 neurons in the first layer and 2 for the binary classification and 4 for the fault classification between the 4 known faults. So we trained first the autoencoder using the reconstruction loss from the autoencoder and the KL divergence loss, which is in the latent space. And then we trained the classifier. We did that twice, once for the first one and once for the second one. The one-class support vector machine is just a simple standard support vector machine, which we use to see if there's an unknown fault. We gave in all the fault data and instructed the model to tell us, do you know this data or not? So we got the hint to the unknown fault. And how did we combine this now? Here you can see the first step, the first variational autoencoder, the fault detection. For the prediction, so this is now how the system was working in the end. For the prediction, we only applied the scalar as data preprocessing. So the scalar we previously fitted to all of the data. Then, we sent the single sample, so no time series methods here. We just looked at each point individually, sent to the VAE with the classifier, and had as a result fault or no fault. If there was no fault, we entered it in the metrics in the results list as no fault and set all the fault accuracies or fault probabilities to 0. If there was a fault, we took this single sample again, inputted it to the second autoencoder and to the one-class SVM in parallel. So in the end, we have the probabilities of the known faults, and down here we have a 1 if it is a known fault and a -1 if it is an unknown fault. So how did we determine the unknown fault probability now? This output is already telling us what are the probabilities for the known faults. But since we have 2 models predicting if it's a known fault or an unknown fault, we have to combine them somehow, which is what we did here on the right side. We looked if the maximum of those probabilities is below 0.98, and if the one-class SVM said it is an unknown fault. If that was the case, we set the probability for the unknown fault to 1. The 0.98 was from trial and error. We looked where we had to set the threshold. Then we checked if the probability for one of the known faults is above or equal to 0.98 and the SVM says there is an unknown fault, then we decided to trust more the variational autoencoder and said, okay, it's 0.5 because the SVM said it is an unknown fault, so that we have the unknown fault at least in the second place. And else we said there is no unknown fault. In the end, we did a normalization of those faults to have the sum of 1. So that is already our solution. And here are some training results, which we did with all the data. So in the end, you can see the accuracies went or are quite high, but for seen data. So this is just a random train test split, 70% training data, 30% test data. And here you can see how the latent space looks like. It looks, or in the first 3 latent dimensions, it looks quite okay. But to have a closer look at how our system reacts to unknown faults, we did another test, and with this test we also did a hyperparameter tuning. So we set in the training data, that's written down here, we have PIC 90, PIM 80, and WAF 105 plus IML. And in the test data, we have the others. So we have unknown amplitudes of those faults then, and did the same again. For the training data, that's no surprise, it looks really good. For the test data, which you can also see in the confusion matrix on the left side. There are some problems. We've seen it before with this WAF fault that might be somehow hard to detect. Also in our case, that is the light green one over here, so it's confused with the PIC fault. We were able to detect the PIM fault really good. And IML, we cannot judge because we had only this one fault amplitude. And we also were able to detect the normal mode, at least in the VAE, so we only have the VAE classification results here. So yeah, the thing is only that we don't know how it will react to unknown faults and unknown data, since it's a purely data-driven method. And yeah, that's so much from my side. Thanks for listening.
So thank you very much for your presentation. So do we have any questions from the audience? Okay, then thank you again. And thanks to everyone who has been contributing to the competition. We're a bit, we have some extra time now, so we have been quick, that's good. So I hope that we have more time afterwards to continue the discussions. So I can say that receiving all these solutions and having the chance to see them and evaluate them was a really nice experience, because as you see here, everyone has tried to solve the problem in a very different way. There are similarities, but there are also a lot of differences. So it was very interesting to see kind of the inspirations and the ideas that you use to approach this problem. So let me see. Okay. This tells more about my Italian than anything else. Can I just... The first one, okay. I'll just do something. Okay, so we looked at all the solutions, we received the code, we received some description of the approach from each participant. Then we did some experiments using the kind of template code that we provided. So what we tried to do here, so each participant got some realizations of each fault. Those are represented by these brownish colored fault magnitudes here. So what we did was that we evaluated using 16 new data sets, kind of testing other fault sizes of the same fault types, and evaluated how it worked for each participant. And the collection had been done in a similar way. I don't know if there had been someone coming late to the session, but just for a recap. So each of the data sets were collected from the same driving cycle. And as I said, it was logged, data was logged with 20 hertz. We injected sensor faults into the control system. The leakage was via control valve. And we start each data set with some fault-free data, and then we injected the fault after some time to evaluate how it worked. So for each data set, we looked at different aspects. We start to look at the false alarm rate. So more or less how many alarms did we have during the fault-free sequence of the data. We looked at the true detection rate. So more or less how many of the samples were truly detected as faulty. And then we looked at isolation accuracy. And this can be done in different ways. We selected to look at when a fault was detected by the solution, how many of the samples were correctly identifying the true fault in this case. And we looked at some different aspects of this. We had a ranking which was fairly similar, but we felt that an important aspect of a solution is that to avoid false alarms, and we wanted to see some emphasis on the isolation rate, to kind of the true isolation. I can say that we have some results. I will show that. We did some sensitivity analysis by adjusting these parameters. It didn't change the results much, or it didn't really change the results. So we felt very confident of using these weights. And we did this computation for all the data sets, not the training data, but for all the black colored sets here. So the 16 data sets. And we took the average over all those in the end. So I will try to summarize some results here, and after that I will present the final results, or the first evaluations, but then the final results. So I will present the results in the same order as the participants presented their contributions. And I try to summarize this in this figure, so I will take a minute just to describe what we see here. So each plot here represents one fault type. The gray regions represents the training data, the kind of fault realizations that was provided in training data. And I've included the results here just for comparison, but that's not included in the valuation. Then we have plotted what I said before, the false alarm rate, the true detection rate, and isolation rate. And to make the comparison easier, but maybe a bit confusing, we took the false alarm rate, but 100% minus the false alarm rate. So ideally, a solution should have everything 100%. That is kind of the perfect performance here. But we can see here, for example, that for the first fault, it's a sensor fault in the pressure sensor mounted close to the intercooler. So it's before the combustion. We see here that we have a good false alarm rate, so very few false alarms except for the extreme faults. When we have good detection rate and isolation rate here. We can also see for the second fault, the pressure at the intake manifold, so it's even closer to the combustion. We see the effect of small faults, I can show here, that the detection rate is lower, but you can see that detection rates increases as you deviate from for bigger fault sizes. But we can also see as an example for the last sensor fault here we've considered is a fault in the air mass flow sensor that good performance is achieved around the training data, but when we looked at for positive faults, but for negative faults, we see that we have good detection performance, but the isolation performance was not as good, but I believe this is a reason is that the data deviates quite a lot. So this is kind of just to illustrate how you should interpret these plots. So this is for Anna Stieber. We see, let's see. For the second contribution, Anselmi and the rest from Italy, we see that we also achieve very good detection and isolation performance and low false alarm rate. We can see some indication here that detection performance is lower for small faults, but the isolation rate is good. We get the third one, Zhu, and we see also some trends perhaps. Something I would like to say here is that the participants have not seen the evaluation results, so they've only seen the training data. But we can see here also that it's fairly good with detection and isolation. There are some cases with this FWAF where there are some misclassifications when we are looking at fault realizations that are far from training data. Then we have the next team. The first author in the list here was SAFEPROCESS. And also here we see a good false alarm rate and detection rate. There were some interesting thing here is that it performed very well, but there were some realizations it couldn't isolate. But otherwise, so it was kind of, it's interesting results here. It's good. We have the next one. Okay. And we see here as well that we have good performance for this first sensor fault. We see fairly good performance where we have training data, but some things happened here when we deviated from training data. We can see that something that you could see in some of the other solutions as well, that detection performance increases with fault size, but sometimes the isolation performance was degrading, but it still kind of works in the classification aspect. So it's interesting here. And the final one, with Silke Merkelbach. We see here as well that we have some good performance. There were some false alarm rate in some of the data we evaluated. So I'm a bit curious here when I see the results from your own presentations that it were some inconsistencies here. But this is kind of, we use the same evaluation method for all solutions. But it's very interesting to see here the performance. So based on this, also I would like to say we did some evaluation on computation time, and we were also thinking that it could be an implementation aspect, or how we implemented, or kind of how we evaluated the solution, but we could see that many of the solutions were very fast. There were one solution that took more time, but it could be an aspect of if it used the GPU and stuff like that, but most of the solutions were more than real time. So try to summarize this. So this is kind of the scoreboard for this competition. So from our evaluations we got this. So the first column is the false alarm rate, as I said. So 100% is the best. We have the detection rate in the second column, and we have the isolation rate in the third column. And the score that we used, we get this order. And so for the third place was Anna Stiber from Poland. So I would like everyone to give an applause. And for the second place, we have SAFEPROCESS and his team got second place. So congratulations. And the team that in our evaluations performed really good was the Italian team with Selmi and Corini and everyone. So a big congratulations to them. So there will be an award ceremony after the conference. So I hope everyone can attend. I will also thank again everyone participating in the competition. It was really nice, really interesting solutions, and really inspiring. The goal with this competition from our side was to inspire more people to look into these problems and we hope that you will continue to improve your solutions, and maybe even more people will have the chance to look into this. We will publish the test data, so you can continue to work on that as well. I've also invited all the participants to come and share their experience and knowledge from this work, to maybe so we can write a paper together and describe more in the details that what everyone has learned. So I would like to end here with some chance for discussions, if anyone has any comments or questions. It's also our first time to have a competition, so we also would like to have some feedback and see what we can do better if we arrange a competition in the future.
Yeah, I would like, in the name of the SAFEPROCESS conference, to no, let me see, I'm far away from the microphone. Yes, to thank everybody, you as the particular University of Linköping, that really at the beginning we were not clear how far it's going to be, and what I say now is that it's an excellent experience, especially for us as people of the SAFEPROCESS, and for the students. I think it's, sorry that we are not a lot here now in the room, but really this is a very good experience, and I suggest the people that we have to do more examples like this. This kind of competition tell us a lot about the possibility and bring the people to work together. Thank you very much. Thank you very much. Please, Eric and Daniel, please.
Thank you for the nice words. Yes, we have the microphone over here.
So basically, I see on my results, on our results, that the true detection rate is the lowest possible, because it's 83% respect to the fifth group, maybe did a little bit worse. But I think you will publish the test data right after the competition. Yes. That can be, but I'm not sure, the time to detect the fault, because our algorithm has a time forgetting factor that is really high, really close to 1. So before the parameters change from the nominal region to the fault region, so outside the nominal region, takes time, and the time of faults is not detection of the. But if I increase the data set, so I remove this transitory of the data, then probably the true detection rate would be higher. I don't know, I would test.
Yes,
but,
it's a very good comment. So we looked at the solutions from many different aspects. So in the end, it was a question how to measure and how to value, kind of how do you measure all of these aspects. So in the end, we saw that some of these correlated quite a lot with each other. So we decided to have a focus and try to the most dominating one. And we had a weight that we had kind of, and looked at how would the result differ if we change some of the parameters in our score function. And we saw that it was stable. Kind of, it didn't affect the ranking much. But of course, we hope that you will continue to use the data and continue to evaluate and I mean, there is all these factors could happen. Did something happen during the evaluation when we evaluated compared to you and so on? So it, for us, we tried to do it, and it was very fun to see all of your contributions, all of your ways of trying to approach the problem, and you did it in very different ways. So it's also inspiring for us to see other ways of doing it. But I hope that you will kind of take this and continue this and improve.
No, I have to thank you, because 26 data set about 24 different fault conditions is not something you can find everywhere. So that data set are pure gold. And personally, I use that also to validate an approach that I'm putting in my master degree thesis. So, and it is difficult to find faulty data sets that are that clean, that so well measured. So thank you, because sharing that to everyone is, for everyone is something really important. Thank you.
Yeah, well, maybe you can stay, because I have a question for you. That's why I came before you left. Because I was wondering what, well, pretty much anybody, but maybe you as the winner thinks why the solutions worked so well or did not work so well. And if I remember correctly, one of your slides, you did some kind of feature engineering, might say, because you took the square and all that. What do you think was, I mean, how much did that contribute to the performance? It's hard for you to say because you didn't have the test set. You can only tell from the training set, but yeah.
So basically, applying our method of feature selection was a way to have a simple solution, not a so hard solution like neural network, which is difficult to manage and to test and to have performance. So basically, if you see the results in test are better than the results I showed in the slides, because just adding one data set for calibration of the solution increased the false alarm rate from, I was having 9% of false positive, here is 0. So having chosen that features probably is the way that having that simple representation, that simple model, and that was, we can say, having the control of the variable will produce the result of having consistency between the results on train and test and validation and the final test results. So I think the contribution is probably it's the key of our result, not only mine. I'm the only one here with professor, but we worked in 4 to this thing, and it was the main thing we focused on, and probably the key of the winning. Who knows?
Yeah, you did. When I saw the plots, when you showed them, and there was this, well, -5%, +5%, and some models, some solutions were kind of performing asymmetrically. I was thinking maybe all they would need would be some square features, because then you get rid of that asymmetry. But they would have to test. No, I didn't. Too bad.
Thank you. I just want to say that it's 1:15, so the session is officially closed. But if you're interested to discuss more, I would like to have some more words with the participants today. But otherwise, I would like to thank everyone for coming here and listen, all the participants who contributed and shared their experience. So a big applause for everyone. And thank you.
Yeah.
All right. So can I have your attention, please? I would like to take the opportunity to tell a little bit about our benchmark. We presented it previously today. For you who didn't attend that sessions, we had presented a benchmark where we wanted to address the problem of how do you perform diagnostics when you don't have representative data and when you have some physical insights but you don't have a perfect model. So how do you do this in a smart way? And we had 6 really interesting participating solutions trying to address these problems in very interesting ways. So it was really fun to be arranging this competition and seeing all inspiring solutions. So I would like to give kind of the awards for this competition. So just to show you who haven't seen it, so these are the participating teams. And let me see. Now I did something. No, it seems to work. So what I would like to is, I know one team had to leave, but for the rest, I would like to everyone to come up one at a time to receive your diploma. I think I can just. No, but it's I can stick with that. So
Okay.
We'll just, yeah. So first, I would like to have the team. Let's see if you have the name here. So first, I would like to have the teams Hao Bin-ke and Jiamin Xu, or representatives for those 2 teams, to receive a diploma from us. It was really interesting results and interesting solutions. I hope to see some improvements or continued work in the future. So a big applause for the participants. It was really good work. So I should have prepared this, sorry. So let's see. Oh. So I would also like to mention the Silke Merkelbach and her team. She couldn't attend now. So next I would like to have the 3rd place of the competition in our evaluation. So Anna Stieber-Bettley, if you could please come on stage. Congratulations, good work.
Thank you.
So, and then I would like to have one from SAFEPROCESS and all, the 2nd place in the competition. So, of course. Congratulations, good work. So. And finally, I would like to welcome the team, Anselm Medal, to please come on stage. So, congratulations, good work, really impressive. And again, thanks everyone who participated. It was really good, interesting results, and I hope to see more work in the future. And also for the rest of you, we are publishing the data, so you're free to use it if you want to participate yourself or kind of you want to evaluate and see if you want to try out these aspects and want to try your algorithms. So I hope to hear more from you, and if you have any questions regarding the competition, don't hesitate to contact us. So before I leave the stage, I would like to thank everyone again participating in the competition, and thank you for a good conference. Okay, thanks.
No, I think I don't have a special.
Okay, thank you. Good afternoon, everyone. So we are arrived at the end of our journey. I hope you enjoyed the conference, all the social events, and also the city. You have time, or maybe if you are staying before leaving, for coming back to your countries. I hope you will have time to visit the city and to enjoy also some time. And so we are arrived close to this 12th symposium. You know, or at least for those who did yesterday evening were not participating in the social dinner, the next SAFEPROCESS symposium will be in 2027 in Delft. It will be organized by the group working in Delft. So I think that it could be a good opportunity for this benchmark, which was hosted by this symposium, that maybe as we did for those of you who remember, it was the benchmark on the wind turbine, because it was continued during the SAFEPROCESS 2009, Mexico 12, the World Congress in South Africa 2014, and then also there was a small achievement or a summary during CDC in 2015. So it was very useful, and especially now that the data of this benchmark will be available online. So I think is a very good opportunity for also publishing and demonstrating some solutions applied to this data. And also another important announcement that was done yesterday evening, that the next SISTOL conference, the SISTOL conference is another event which is sponsored by IEEE. In the past, it was co-sponsored by also IFAC. We had two co-sponsors of this conference. I don't know the number, but should be almost of the same size. Of about we had,
I think so.
With respect to the report at the first day, Christina we had the updated number of the participants, which is 187. So I think is a very good number. I don't know, maybe only the SAFEPROCESS in Poland perhaps did better.
I think the average is more or less between
the size of
something like this.
So I'm also very happy that I was able to organize this symposium, because I remember about more than 10 years ago when I think we were discussing where organizing I'm afraid that Vicens has already left, but we were discussing with the other guys of like Ron Patton, where we could have organized the SAFEPROCESS in between Barcelona and Mexico. And when I proposed Ferrara, I was told that perhaps by that time I was too young to organize such a symposium. So maybe now it means that I'm not so young because this year I was able to bring also this symposium here for the first time. So it's a very good also result, and I'm proud that you were able to attend this symposium and also to attend all the sessions. So I think
without any other comments.
Thank
you very much,
I want
everybody.
to give a special thanks to Christina that yesterday evening, unfortunately, will be her last
Yeah, I say
SAFEPROCESS.
this is my last event in which I work for the SAFEPROCESS. I
So
maybe attend as a visitor, but not anymore.
Of course, you can invite I think,
okay,
but you will be always with us.
Thank you very much, the support for all the associate editor, the keynote speaker, and the audience. Without you, we couldn't do anything. We are a society together, and thank you very much for everything.
And also to the people that are not appearing anywhere, but they are working behind, like the people they are streaming the event. Everybody, all the technicians who helped us very proudly, and they worked very hard to maintain everything in a always working way. When somebody unplugged by chance a wire and the streaming was lost, or the network, as it happened. So thanks again for your participation, and
see you in 3 years and then.
I wish you also a safe journey back to your country. Thanks again.
Bye-bye.